Okay, so hello everybody, first of all. I hope you slept well. We start this morning session with David Wiygul. It's a pleasure to have David Wiygul here in Pisa. He recently moved to the University of Trento, so congratulations. He will talk about the uniqueness and Morse index of minimal surfaces in the spheres and in the ball. So please, you can start your talk.
Okay, is the volume okay? Seems okay. All right, well, thank you very much for the introduction, and thanks to all the organizers for the kind invitation. I'm really happy to be here, and all the talks yesterday were fantastic, so I'm looking forward to today's talks and tomorrow as well. For my own talk, I want to tell you about a collection of different projects I've been involved with, mostly 4 projects, but I'll mention some more recent things very briefly as well. So these are projects in 2 different collaborations, which are ongoing over the last 4 years. And the projects have to do with somewhat complementary material, which is why I've grouped them together. And so 2 of them, the earlier 2, were joint work with Nikos Kapouleas, who was also my PhD advisor and has become a collaborator. And those projects have to do with closed minimal surfaces in the round 3 sphere. And the more recent projects, especially these 2 that I'll be focusing on, are joint work with Alessandro Carlotto and Mario Schultz. And those have to do with free boundary minimal surfaces in the 3 ball. And there are some, as you may or may not know, there are parallels between the 2 settings, and there are other reasons to link the projects, which I think will become clear in the talk. Let's see, maybe I should also say before starting that I'm not trying to draw in this talk any kind of logical links between uniqueness phenomena and Morse index. It's just that in these projects, we study certain specific surfaces, and we can say things about uniqueness or non-uniqueness and things about the Morse index. Let's see what else. Oh, I should also say that all of the wonderful pictures in the talk are due to Mario Schultz. So to clarify, not all of the pictures are wonderful, but those which are wonderful were created by Mario. So credit to Mario for that. Okay. Great. So I'm going to start the talk by setting the stage and just giving some context for a few slides, tell you about some old problems that are interesting, and then I'll start to talk about some examples in the ball, and I'll move on to focus on the projects in the 3 sphere, which are the older ones, and so I'll be brief with those, and then I'll spend more time on the projects in the ball. Okay, so starting at the beginning, setting some notation and describing the stage, as I was saying. So on the left, I'm going to have things that have to do with the 3 sphere, where we're going to be looking at closed minimal surfaces, so just the unit sphere in R4. And on the right column, we're going to be looking at the unit 3 ball in Euclidean space. Okay, and in both cases, I'm interested in compact surfaces which are embedded. So maybe occasionally I'll mention things about surfaces which are just immersed, but I'm going to assume embeddedness throughout. Okay, and in the closed case, well, I assume, in the 3 sphere, that is, I assume the closed condition. So there's no boundary. In the free boundary case, that is in the ball, I have the free boundary condition, which means that the surfaces I look at, they do have boundary, but their boundary is required to lie in the 2 sphere, the boundary of the ball. Okay, and we're looking at critical points of the area functional in both cases. So in the closed case, that's just the condition of mean curvature vanishing. Well, in the free boundary case, there's an additional condition, right? Both of these conditions come from the first variation formula. So the additional condition is that if you're a critical point, then not only must the mean curvature vanish, but also you must have orthogonality, orthogonal intersection of the boundary. Okay, and because we're looking at critical points, we can talk about, we can look at the second variation and talk about Morse indexes. Of course, we'll be doing in the talk. So the second variation is governed in both cases by the Jacobi operator. So this is the Laplacian plus the squared norm of the second fundamental form. And in the case of the 3 sphere, there's an additional term coming from the Ricci curvature of the sphere. In the case of the ball, right, the Ricci curvature doesn't show up, but now there's a natural boundary condition which comes along with the Jacobi operator, which is basically the linearization of the free boundary condition. Okay, in both cases, the Jacobi operator supplemented in the case of the ball with this boundary condition, it gives rise to an elliptic self-adjoint operator. So we can look at its its real spectrum. We have nullity, which is the dimension of the kernel, and the Morse index, which you can define as the number of eigenvalues. Excuse me, the number of negative eigenvalues counted with multiplicity. Okay. So let's look first maybe in the ball. The examples here are easier to draw. And so we'll start with the two simplest examples. So we have the equatorial disk and the critical catenoid. So there's if you look at catenoid centered at the origin, there's a unique scale so that you're going to have the orthogonality, the orthogonal intersection. Okay, and these are the only rotationally invariant examples. And of course, so when I say the only examples, you can apply rotations and you get other examples, but up to ambient isometry. So these are the only examples which are rotationally symmetric, and they were also the only examples known until relatively recently. Okay, but around 2010, actually, I didn't do a good job in the talk at including dates, but somewhere around there, starting with the work of Fraser and Shane, we had many more examples. So they constructed infinitely many more examples, and subsequently there's been, they spurred a lot of activity in the field. So there are many examples now with the constructions coming from different perspectives. I only have time in this talk to tell you about a few of them. So I'll just put them there. But even though we now have all these examples, there's many questions open. Even the basic question of which topological types are realized at all is not been settled. Can you remind me when I started, actually, because we started a little bit late. Just okay. All right, thanks. Yeah, so here I have a table which I think which I stole from Alessandro, actually, which I think is still up to date, I believe, the state of the art. So the columns, you have the genus, right? So the topological type for the kinds of surfaces we're talking about are parameterized by the number of boundary components in the genus. And so you can see in the case of genus 0, we have infinitely many examples, starting with Fraser and Shane, actually. And for one boundary component, we also have infinitely many examples. That's work of Carlotto, Franz, and Schultz. But there are a lot of question marks, right? So in some cases, we have existence only if you take the topology to be large, either the number of boundary components or the genus. And that's because either these are constructions by gluing, and I'll be talking about a gluing construction a bit later, and you need that in order to ensure that the gluing construction goes through. Or maybe they're by min-max, but you don't have control of the topology unless you assume it's large. Okay, so a lot of question marks, and this is in stark contrast to the analogous situation in the three-sphere. So let's look at that. So here we have more cartoonish pictures. So in the three-sphere, we have kind of analogs of the equatorial disk and the critical catenoid. We have the totally geodesic spheres, or the great spheres, and we have the Clifford tori. So a Clifford torus is, you can define it as the set of points in the three-sphere, which is equidistant from a pair of great circles in R4, which lie in orthogonal two planes. And I've drawn it as kind of a catenoid, so there's some quotienting there, but I don't have a precise picture in mind. It doesn't matter, or coordinate system rather. Okay, so these are all of the rotationally invariant examples. Okay, but already in 1970, Blaine Lawson settled the question of which topological types are realized. That they're all realized. He constructed examples for every topological type. So of course, now that we have no boundary, the topological type is described just by the genus. So it's clearly less complex in some sense. And so how does Lawson's construction work? Well, so first of all, actually in the same paper, Lawson, from around 1970, Lawson constructed many examples, many immersed examples too, but I'm just talking about his embedded surfaces in this talk. And so this family of embedded surfaces, CMK, is labeled by two discrete two integer parameters, K and M. And you have existence for all K and M greater than or equal to 0, and you get a surface of genus K times M, the product. Okay, and the way that the construction works is Lawson starts by solving a plateau problem. We're not looking at the plateau problem using currents, in the sense that John Marco was talking about, but in a more classical sense, it doesn't really matter for the talk actually. But here's the setup. So you take two great circles in the three sphere, and you take 2 points on one circle, so these 2 points, and you take 2 points also on the orthogonal circle with some prescribed spacing between them, and you take also the quarter great circles that join them from one circle to the other. So you got these white pieces are supposed to be quarter great circles. And then Lawson showed, following Mori, that you can solve the plateau problem in this sense, which is like the Douglas sense, basically transported to Riemannian manifolds. And you get a disk solution. And then, because these are quarter great circles, you have a reflection principle that tells you that you can extend this, and you can do the reflection iteratively, and you can close up to a nice closed surface, provided that you take the spacing that is equivalent to the angles here at the vertices appropriately. It should be pi over some integer, and the k and the m are the integers for these vertices. Okay, so that's the construction of Lawson, and in that way you get every possible topological type. And since then, there have also been many other constructions, again by different methods. So there are methods kind of like the Lawson method, where you solve a plateau problem or some kind of boundary value problem, and then you extend min-max constructions and also Boolean constructions. Okay, so many examples, and you can start to ask more refined questions. So if we can let's call MG the space of closed embedded minimal surfaces of genus G, is known by there's a well-known result of Choi-Shane, which, well, in particular implies that in the case of S3, this space of surfaces is compact in the CK topology. And actually, for very low genus, we can say much more. So we know that for genus 0 and 1, actually, there's only one example up to congruence, again, up to ambient isometries. So this is respectively a theorem of Almgren, which says that in fact you can drop the embeddedness assumption in the case of genus 0, and you have only the totally geodesic spheres. And then a harder result of Brendel. So for a long time, this was a conjecture of Lawson that if you assume embeddedness, that you have only one genus, one example. The Clifford torus, there are many, infinitely many immersed examples. Okay, but now this is a theorem of Brendel as well. Okay, so we have a classification for low genus. Okay, it's also interesting, and it's been studied for decades. You can look at what are the minimal surfaces of low Morse index. Okay, and so for the sphere and the Clifford torus, these are rotationally symmetric examples, and it's a totally elementary problem to compute the Morse index. In these cases, you have 1 for the sphere and 5 for the Clifford torus. Okay, but it's a very interesting result of Urbano that actually these are the only examples of index at most 5. Okay, so naturally, it'd be interesting to say, well, what about higher genus? What examples do you have? What can you say about that, or for higher index? And I don't have any answers to that, but I want to talk about some sort of, I pose these questions as kind of motivation, of many possible motivations. So the first project that I wanted to tell you about, the results really are relating to the Lawson family of surfaces. And they have to do with uniqueness questions and index and nullity. So first, maybe the index and nullity results. Okay, so with Nikos Kapouleas, we showed for a particular subfamily of the Lawson. So remember that the Lawson surfaces have these 2 integer parameters, k and m. But for this particular result, we fix one of the parameters to be 1. Okay, and then you get every possible genus still. You allow the other parameter to be free. And if we assume G to be at least 2, okay, so G equal to 1 and G equals 0, I don't think I said it, maybe it was on a slide, but the Lawson surfaces include a special case as the Clifford torus and the totally geodesic spheres. So we'll exclude those cases. So as long as G is equal to at least 2, we were able to compute the index of the Lawson surfaces exactly as this very nice formula 2G plus 3, which also happens to hold for the Clifford torus, but not for the spheres, and nullity equal to 6. Okay, yes, I already said that we exclude those cases. G equals 0 and G equals 1, those have continuous symmetries. It's a very different story. Okay, and so the Lawson surfaces, they're constructed somewhat abstractly, so it's not explicit computation. Here, maybe I'll just say a few words about the proof, and I'll go into slightly more detail when we look at the ball, the similar applications or similar arguments in the ball. Okay, so right, so a very important tool in the proof is an adaptation of an argument that Montiel and Ross used in studying the index of complete minimal surfaces of finite total curvature in R3. And the tools are very basic. Again, maybe I'll give you some sense of the flavor of the arguments, which I'm sure you've probably seen arguments like them, I'm pretty sure. But anyway, so the arguments are quite basic, but they apply them in a very effective way. And so very roughly speaking, the idea is to get lower bounds and upper bounds, and they're able to do it in a way that the lower bounds and upper bounds agree, and we're able to do it at least for this subfamily of the Lawson. So the lower bounds, the basis for them is you take your surface and you take some partition of it into subdomains, and you look at the Dirichlet problem. So for the Jacobi operator on these subdomains, and you look at the index and the nullity, and if you get those values or some lower bounds for them, then you can deduce from those a lower bound for the index on the whole surface. Okay, and for the upper bounds, it's a somewhat similar story, but now you want to look at the Neumann condition on the interfaces of the surfaces, of the subdomains. And in this case, you get upper bounds from upper bounds on the index and the nullity of the subdomains. Okay, and so in the case of the Lawson surfaces, the partitions that we look at are sort of dictated by the symmetries. So you have, for example, you have many reflections through great spheres, and so those great spheres cut the surface in a very natural way, and you can look at the ambient the Killing fields in S3. Those generate Jacobi fields, and it's possible to get enough information to make this kind of argument go through. Okay, just to say very roughly what some of the strategy is. Okay, and then the other result I wanted to mention for the older projects is this characterization, so a uniqueness result. So I was talking earlier about the results of Ongren and Brendel, which are really spectacular, that you get a classification for low genus, or your uniqueness in this case for low genus. Okay, well, you certainly cannot expect uniqueness for all genus. If you look just at the Lawson surfaces, in fact, remember that the genus is given by the product of the parameters. And maybe it's not obvious from what I said, but surfaces like this one, where you have k equal 1 and m equal 4 versus both equal to 2, they have the same genus, but it's very easy to see that they're not congruent. Maybe not from what I've said, but it is very obvious that they're not congruent. Okay, so what Nikos and I did is we gave ourselves a much stronger assumption. We also assumed the symmetry group, actually a little bit less than the full symmetry group in some cases, but essentially the full symmetry group. And if you do that, actually, that's enough to determine the Lawson surfaces. So you have a closed embedded minimal surface with the same genus as some Lawson surface and also the same symmetry group, or nearly so. Then you know that your surface is that Lawson surface actually was congruent to it. Okay, so the proof here, again, say almost nothing, but at some point you reduce the proof basically to the uniqueness of the generating disk, the solution to the plateau problem. Yeah, so and that's proved using the maximum principle and a certain Killing field in S3. And I want to mention also that we have some ongoing work where we're looking at applying, trying to see if we can get the somewhat similar, at least, characterization for some other surfaces. There's a family constructed by Trey and Saray, which is also some of those surfaces are constructed by solving a plateau problem first. And at the moment, we have only a much weaker result, but we're still interested in pursuing that. Another question, which is very interesting to me anyway, is if you can, focusing again on the Lawsons, if you can actually significantly reduce the assumptions in terms of the symmetry group. So those Lawson surfaces have, it's clear from the way I described the construction that they have these symmetries you can reflect through great circles. But they also have, well, I mentioned they have symmetries with respect to reflections through great spheres as well. And I think that it's plausible that you can remove the assumption of the reflections through great circles, but we can't prove that. Okay. All right. So now back to the three ball, which will have to do with the more recent projects. So first, analogously to the result of Angren, we have this result of Nietzsche that the totally geodesic, totally geodesic, but I mean the equatorial disk is the only free boundary minimal surface of its topological type. And also, well, we have, okay, so there is no analog of the Brendel theorem, but there's an analog of the Lawson conjecture. So it's conjectured that the critical catenoid is the unique embedded annulus, but it's not known. Okay. So you could ask, well, what if you strengthen this by symmetries? Could it be that you always have uniqueness if you assume that would be a somewhat naive assumption, but could it be that you always have uniqueness if you assume not just the topological type, but also the symmetry group? So you can turn that around and ask, are there pairs of twin free boundary minimal surfaces? So I mean twin in the sense that they have the same symmetry group and topological type, but maybe not identical twins in the sense that they're not congruent. So with Alessandro and Mario, we were able to answer this last question affirmatively. So there are such pairs. And so we did this by constructing a family, which is a twin to a family that was already known. So the family that was already known is one which is constructed by Capillary and Lie. And I have also here Ketover. So because there's another, so the Capillary Lie construction is by gluing. There's another construction by Ketover, which is by min-max. And I think it's extremely likely that these are the same surfaces or congruent surfaces, but actually it's not known. And there's some difference. There's an important difference in terms of the result from our point of view, in that Ketover, I think it's not known that his symmetry group is the same as the Capillary. So I really have in mind the Capillary construction because we know a little bit more about it, or I do anyway. Okay, so what does the Capillary construction say? For every G sufficiently large, you can find a free boundary minimal surface which is embedded and has three boundary components and the prescribed large genus G. It also has this particular symmetry group, anti-prismatic group. I'll explain what I mean by that very shortly. Okay, and also we have this property that as G goes to infinity, the sequence of surfaces converges in the manifold sense to the singular limit, which is the union of the critical catenoid. That's what I mean by K, and the equatorial disk, which is what I mean by B2. Okay, so anti-prismatic symmetries, it's not really even a big deal for the talk, but it's the symmetry group of an antiprism. So this is here on the top face and the bottom face are M-gons, but they're anti-aligned. They're kind of totally out of phase. And so this symmetry group has two generators. It's generated by reflection through this the x-axis in the picture, and also through this bisecting blue plane. Okay. And our twin family has, well, the same topological type and the same symmetry group. That's by design. But the varifold, you can distinguish them by their varifold limits. So in this case, this family converges to the union of the equatorial disk and not the critical catenoid, but some other catenoidal annulus. So it's a piece of a catenoid. And also its mirror image. So its reflection through, not quite what I wrote, but it's the same as its reflection through the plane Z equals 0. And so what is this catenoidal annulus? Well, it's the intersection with B3 with a complete catenoid, which has axis, the Z-axis, but it's not free boundary. Well, one circle of latitude, it is you have orthogonality, but the other circle of intersection is Z equals 0, which is the significance of the 0 subscript. And you have some other angle there. It's not pi over 2. I don't remember what the angle is, but it's not pi over 2. And so here's a picture, or a cut in half picture of the varifold limit. So in the middle you have the disk, the equatorial disk, And on top, you have this K0. So it's not clear from the picture, maybe, but that's not a, well, I think it is pretty clear, maybe, but it's not a right angle there, and it is on top. Okay, and the mirror image on the bottom. So here are the two surfaces side by side. So for some particular value of G, anyway. And so again, we need G large for the construction, for both of these constructions to work, actually. And so these pictures that Mario produced, we're not saying that we can produce the surface with this particular G. It's just for visualization purposes. We suspect that they do exist, though, for all G. Okay. So maybe now I can tell you a little bit more in detail about this result, at least, so how the construction goes. So yeah, this is not a collaboration with Capillary, but we do use his kind of framework for gluing constructions. More specifically, it's a desingularization construction in the sense that, well, we have the singular limit. So we do the construction by starting with the singular limit, and you cut out a neighborhood of the singular curve of intersection, which is the equator in this case. And you're going to glue in some other surface, and you're going to you're going to get some surface which is approximately minimal. And well, depending how you do it, maybe also you lose the orthogonality near that equator, and then you're going to perturb the thing to be, by PD methods, to be an exact free boundary minimal surface. That's the idea. Yeah, so we start with the singular limit, which we call the initial configuration. And I think I just said you cut out the circle, and we'll glue in something else, which I'll describe very soon, right now, in fact. So the desingularizing model that we use in this case is it's a complete surface, complete minimal surface in R3. And it belongs to a large family of surfaces that were discovered by Hermann Karcher, and they generalize these classical surfaces, which you may know of Shirk. Well, I guess Shirk has a number of classical minimal surfaces associated with his name, but I mean these singly periodic surfaces. So the surfaces we use are singly periodic in R3, and we're going to wrap the axis of periodicity around the circle. That's the idea. Okay. Well, we're not going to use the whole tower. It's a free boundary problem, so we're going to cut it in half, actually. Okay, so here's so the way that I'm thinking of the coordinates is the z-axis is going to be the axis of the periodicity, and this is a projection onto, say, z equals 0 of the whole surface, and it has the complete surface has six ends, and the ends are all asymptotically planar, and one of the ends. Well, two of the ends actually, they lie exactly in the x equals, excuse me, the y equals 0 plane. And the other four, they don't. There's some angle, and the angle we pick actually is the same as the angle at which that K0 intersects the ball B2 at the equator. So it's that same angle. So these Karcher-Shirk surfaces come in a large family, and you actually have the freedom to pick, or a lot of freedom to pick the angle, actually. So that dictates the angle. Okay, and let's see. The x equals 0 plane is actually a plane of symmetry for the surface, and that's important for the construction. So we take actually just half of the surface, lying in, say, the x greater than equal to 0 half space. And yeah, so here's a more, I don't know, here's a picture of a portion of the surface, right? The z-axis is the axis of periodicity again, and when you cut, you get this this kind of oscillating boundary, and now we have just these three ends. Okay, so what we do is we're going to cut out that neighborhood of that S1, and we're going to glue in a copy of the tower, which I'll describe in slightly more detail in a moment. Right, and well, you could go about this this step in different ways, but the way we do it is we choose to do the gluing in such a way that we have orthogonality. So the surface that we're going to produce, which is called the initial surface, or this kind of first step of the gluing, it's going to satisfy the right boundary condition, so it will intersect the sphere orthogonally everywhere, but it's going to have some non-zero mean curvature. Okay, and so, well, there's a lot of this. There's a lot of freedom. Some things are important to get right. Let me just tell you very roughly what we do. So first, there's going to be a discrete parameter m for the construction, which is actually going to correspond to the genus in a very direct way, which is on this slide in a moment. So m is going to have to be taken large, but you can imagine trying to do the construction for any m. So for a given m, what you do first is you scale the tower down by a factor of m. And you're also going to truncate it. So the scaling by the 1 over m is that's the precise scaling you want to do. The truncation, it's not important to do this m to the minus 1 over 4 that I did. The point is you want to do the truncation in such a way that as m grows, you're going to include more and more of the surface. So then the limit you're getting at the natural scale before you blow down, you get the complete tower. But you also want to do it in such a way that when you scale down, that you're getting the surface that you get lies in a smaller and smaller neighborhood of S1. So that's really the thing. And then we apply this map, which is really just a variation of spherical coordinates. So now the x coordinate so you're starting with the tower in Euclidean space, and you're going to map it into another copy of Euclidean space so that it maps so that it's wrapped around the equator. And basically you're having x be the radial spherical coordinate, but x equals 0 is going to correspond to the sphere rather than the origin, and increasing x goes inward. And y is going to correspond to the coordinate that goes around the z-axis. And let's see, z is going to be the angle of inclination from z equals 0. So essentially standard spherical coordinates. Okay, and this does the job of realizing the boundary condition that we decided we wanted to preserve. You could do it in a way where you're a bit less careful about what happens at the boundary, and you could treat that as something to perturb later on, as long as you don't create too much error in the process. Okay, and then finally, so now you have this very small, well, for m very large, you have a very small copy of the Parker-Shirk tower wrapped around the equator, and then you're going to take the 3 ends that you have, and you glue them, and you smoothly interpolate to the 3 components of the singular configuration. So there's one end which gets glued to B2, and the other 2 to the 2 catenodal annuli. Okay, and by taking m larger and larger, you're going to control the error you get. So by error, I mean not just the mean curvature that you get, but actually the way that you can understand the construction is you compare. You have comparison, geometric comparison for, say, the second fundamental form, and the induced metric for for regions of the initial surface that you create, and you compare those regions to these models surfaces. So either one of the annuli, or the disk itself, or the tower. Okay, and so in the case of the tower, you need to blow up first to make the error small, but in the appropriately scaled sense, by making m large, everything gets better. You have better and better understanding of the surface, and smaller and smaller mean curvature after you scale appropriately. Okay, so then the next step is to try to perturb away the error. So this is a PD problem, but it's a perturbation problem too. So it's essentially a linear problem, right? If you can solve the linearized problem, then you expect by inverse function theorem or some variant of that you're okay. Okay, and so this is global. So well, I mean, at the bullet, it's meant to be a global PD problem. So yes, absolutely, yeah, right. That's right. Yeah, it's a full boundary value problem. Yeah, and so if you arrange for the orthogonality as we do at the beginning, then you're imposing. It depends how you set it up, but essentially you're posing a Robin condition, oblique boundary condition. That's right. Yeah. Okay, and so I think I already mentioned this, but yeah, it's a global problem with boundary condition, but you're going to understand it. I mean, after all, you built this by gluing it, so you're going to try to compare region-wise the surface to the things you built it from. So the tower, or these or the disk, or one of the annuli. Okay, and the point is that all of those are you can understand the corresponding linearized problems. So you're looking at the Jacobi operator on those. And the tower is certainly the most complicated, but it is manageable. Okay, and then you can glue together, so you can solve kind of region-wise, and you can glue together. You can iteratively solve. So You define the regions in such a way so that there's overlap, and you also need to arrange for decay from the towers, from say the tower regions onto the other regions. And this decay, well, is needed for other reasons also, but it's needed so that, in particular, so that you can make this iteration scheme converge. So you solve in one region and then the other regions, and you pass the error back and forth. And because of this decay, and also by taking m large, you're going to be able to control that, to kill that error. Except, so I said you can understand the linearized problem, and you can understand it, but there are obstructions. There's co-kernel. So in particular, there's co-kernel on the towers. And the co-kernel comes, analytically, it comes because you are imposing this exponential decay actually along the wings, which you need, but it gives rise to this co-kernel. So there are obstructions. Okay, and sort of more generally speaking, one expects obstructions to be induced from the ambient killing fields. But maybe I won't say anything more about that. So we handle this following this approach, as I said, of Capillary, and the idea is to handle these in a very geometric way. So the co-kernel you can understand, so you can encounter it purely analytically when you're looking at the problem on the tower, but you can interpret it more geometrically, and you can build into. So you go back to the construction of the initial surfaces. So there was this one discrete parameter m, but you introduce a real parameter. Well, as many real parameters as the dimension of your co-kernel, and generally. In this case, we have a one-dimensional co-kernel, so we introduce one parameter. And the parameter, I mean, generally speaking, it builds into the surfaces kind of repositioning of the blocks relative to one another in such a way that you generate mean curvature, and you generate the mean curvature that you need to control the co-kernel. That's essentially the idea. So in this construction, right, in this construction, yeah, I think I mentioned that the co-kernel arises from the analytic point of view on the towers. And what you do is you actually, so in fact, we replace the K0. I don't include it in the notation of the slides by K0 is actually a member of a family of catenodal annuli where you always have this free boundary, this orthogonal intersection condition at the top circle, but the lower circle is allowed to move. You don't impose that condition. You take whatever angle you get, but you raise and lower the height. Actually, we just need to raise the height, I think. Okay, and as you do that, but you don't change the tower. I mean, you have to interpolate. But in doing that interpolation and changing that parameter, you have a certain mean curvature that you get, which is in the direction of the co-kernel. That's the idea. Okay. So that's sort of a summary of the most important features of that construction, and also that we get as kind of a bonus of the construction. So there's an easier construction that you can do, where you throw away the B2 in the equatorial disk in the singular configuration, and in this way you can construct genus 0 examples. Okay, again, so genus 0 with n+2 boundary components for n, some prescribed but large integer. Okay, so no twins here, just new examples. Okay, and so I have about 20 minutes or something like that, roughly. Okay, great. Okay, so now let's look at the index, Morse index of free boundary minimal surfaces a little bit. So what's known as of now? Well, the index. So we have the rotationally symmetric examples, which are somewhat simple, but already the boundary condition is more complicated. So there are elementary problem. The disk is an elementary problem, but the critical catenoid is not. It's not obvious how to do it, but we do have the result from 3 different papers. Actually, we know that the index of the critical catenoid is 4. And until very recently, so over the summer, something like July, maybe, we now know by the result of two different papers, sort of jointly, that there is some free boundary minimal surface which is embedded and has index 5, but I don't know exactly what it is, but we know that there is one, and those are the only values that we know, as far as I know, the only values that I know of for the index. Okay, So in the same paper with Alessandro and Mario, where we do the construction I was just talking about, we also have a section with some nice numerics and conjectures. And so on this table, I'm plotting. So this is not rigorous. This is done with Brache's surface evolver software, if you're familiar with that. So I think this is very interesting and suggestive, but this is just sort of numerical evidence, nothing we've proven. So on the horizontal axis, we have the genus, and the vertical axis, the Morse index. And I'm plotting two different families. So in the blue, I'm sorry, I guess this is probably too low for many people where I'm pointing, but the blue one is the new surfaces, the one with the 3 boundary components and large genus, which I was describing earlier. And the green one is the twins, the earlier known twins, the capillary or possibly the Ket-over surfaces. And it looks like so the genus we plot for low genus, not high genus, and the surfaces are known rigorously to exist only for large genus. But if you just look at what we have here, it looks like the capillary satisfy this really nice linear bound, which looks somewhat not bound, but linear formula, which not unlike the computation that Nikos and I did for the Lawsons. Very intriguingly, you don't appear to have that linear behavior for the new twin family. But of course, you could ask what happens as the genus grows larger and larger. So this is something I'm very curious about. I'm really interested by the wobbling compared to the straight line in the other case. Okay, and then also I want to show you here the bonus family in the blue. So this is the new genus 0 examples, which also look, except for maybe some exceptional very low genus values, to follow a nice linear formula in the number of boundary components. And then in green is a family which, well, maybe showed up on a slide, but I haven't introduced. This is the well-known family of Folia, Picard, and Zolotareva, which is another family produced by gluing. And show you a picture here. So yeah, as I said, it's by gluing, and roughly speaking, they look like doublings of the disk. So it looks like 2 copies. Yeah, so in the desingularization construction I talked about, you have a singular limit, which is some surfaces intersecting along a curve. In this kind of doubling construction, you have a singular limit, which is the disk with multiplicity 2. So two copies of the equatorial disk, and they're connected. So rather than gluing in a Shirk tower, you glue in very small catenoids to do the construction. Okay, so the picture is for a small number of boundary components. You have genus 0, yeah, and a large number of boundary components is known that the construction will work for. Okay, so in a subsequent, well, starting in that paper, but more in a subsequent paper, we made some effort to see if we could say something rigorous about the index of our new examples. And well, we were able to get some bounds for the index of both surfaces, both lower and upper. And in the case, at least, of the bonus surfaces, the lower bound seems to be somewhat close to the numerics that I was showing you before, but there's a big gap for the upper bound. Okay, nevertheless, maybe this is a later bullet, but I'll put them all up. Yeah, so there are general bounds that I haven't mentioned. So very general lower bounds and upper bounds in terms of the topological types. So the lower bounds by Ambrosio, Carlotto, and Sharp, the upper bounds by Lima, and these are much more general. They're certainly not, don't have these surfaces in mind, and the more general settings even, actually. But the constants that you get, these are improvements, at least on those constants, which were not the focus certainly for the Lima paper, the value of the constant, but seems to be an improvement over what's known. And maybe more interestingly, we're able to get the value for the equivariant index, so not the value for the full index. But so by equivariant index, I mean just the index you get if you look at deformations which respect all the symmetries of the surface. So we know that all of the surfaces in both of these families have equivariant Morse index 2, which has some interesting consequences because of work of Jada-France. So it's known that the Ket-over surfaces have equivariant index 1. So you can distinguish. So as I said, it's not known that those surfaces are the same as the Capillaceae, but you can distinguish the ket-over surfaces not just from the singular limit, but also variationally from our new surfaces. And also, there's an implication for how you could go about constructing our surfaces variationally. You would need at least you would need a 2-parameter. Excuse me. You need to work with 2-parameter sweepouts if you were to do that. Try to do that. Okay. Right. Okay. And so the proof. Maybe I'll try to say a little bit more about the proof. So this also uses this argument of these basic tools of Montiel and Ross that show up in the Montiel-Ross paper. And the symmetries play a very important role for some of the bounds, but also we really exploit the fact that these are constructed by gluing. So it's natural to do that. Of course, I mean that's what we know about the surfaces is how we constructed them, and so perturbation techniques also play an important role. Okay, so maybe I'll say something about the symmetries because that also relates to the methods that were used in the paper with Nikos, and because they're really basic tools. So I don't know if I'll succeed, but I'll try to give you at least a flavor for what's being used. Yeah, so I think I already said that, or I partially said, most of the preceding lower bounds on the last slide, they come from a more general result about how certain symmetries can give you a lower bound on the index in the free boundary setting, and it's also true in the 3 spheres. So yeah. So here I've quoted. Well, it's a part of the result that we have in our paper, and there's an analogous statement for the 3 sphere also, which we didn't state. But yeah. So this uses the proof of this is similar in part to what Nikos and I did. So what's the statement? The statement is, suppose you have some connected embedded free boundary minimal surface in B3. Assume it's not a disk or critical catenoid. And we assume that it's invariant under reflection through some vertical plane. I'm going to pick an axis here. And also invariant under rotation through some angle 2 pi over k for a k integer k at least 2 about the z-axis. Okay, then the index is, you have this lower bound on the index of at least 2k minus 1. Right, so equivalently, you have k planes of symmetry, vertical planes of symmetry, which are equiangularly light equal angles. Okay, so how does the proof go? Well, maybe I'll talk through this a special case, an example kind of. So if you look at this genus 0 family for some particular n, so this is what the picture looks like. I haven't drawn the symmetry planes in the picture, but hopefully they're pretty clear from the picture. You have lots of vertical planes of, well, lots if n is large, vertical planes of symmetry. You have the ones which bisect the boundary components, and also the ones which exchange. If you do the reflection, they exchange 2 adjacent boundary components. Okay, so you have these vertical planes of symmetry, and you have n of them, in fact. And if you cut by those planes, then you cut the surface into 2 n-connected subdomains. And we're going to look at the Jacobi field, so the eigenfunction with eigenvalue 0 for the Jacobi operator on the surface, which is generated by the rotations about the z-axis. Right, so those will give you eigenfunctions with eigenvalue 0, and moreover, because of the symmetries, those functions will satisfy the Dirichlet condition on the boundaries of those subdomains. Well, the boundaries where they meet one another. There's also, because this is a free boundary problem, there's also boundary on the original surface, and there we're gonna continue to impose the natural boundary condition from the first slide. Okay, and so what does that tell you? Just the presence of these symmetries and the ambient symmetries tells you that these subdomains each have nullity, right, with that Dirichlet condition and the natural boundary condition on the rest of the boundary, at least one. Okay, and so what you can do is you can look at any one of those subdomains and you restrict the Jacobi field that you get, and you extend it, then you extend it by 0. So you have a test function which vanishes except for on that subdomain where it agrees with and the original Jacobi field, the global Jacobi field. Okay, and so if you look at the span of these test functions, you can see, right, all of these will have Rayleigh quotient 0 because you started with the Jacobi field. So you can see that the index plus nullity will be at least 2n. Okay, but you can do better than that. So how does that go? So let's actually look at let's throw out one of the subdomains, which we'll call omega. So we have two of these kind of wedges with some boundary also, and if we exclude one of them from consideration, and we're going to look at the span of the functions you get, the eigenfunctions you get on the subdomains by extending by 0, but not that one. So now you have a space of dimension 2n minus 1. And all the elements have vanishing Rayleigh quotient still, but also they all vanish on omega right after you do the extension. Okay, and now the claim is that if you look at the orthogonal projection, right, the L2 orthogonal projection of that subspace V, then it's going to be injective. So you I didn't say the projection onto what? The projection onto the negative let's see, the span of the eigenfunctions of negative eigenvalue. There we go. Right, corresponding to the index for the whole surface. Okay, so I claim that's injective, and that's simply because if that weren't the case, well, then you would have to have an eigenfunction, an exact eigenfunction of eigenvalue 0 in Vy, because you know the Rayleigh quotient is 0, and the orthogonal complement of the span of the eigenfunctions with eigenvalue negative is going to be spanned by the eigenfunctions with eigenvalue at least 0, and so you're caught, and you have to have an eigenfunction with eigenvalue exactly 0, but also it has to vanish on one of these subdomains, and then you get a contradiction for the unique continuation principle for elliptic operators. So maybe you've seen this kind of argument before. Okay, and so that's the argument for 2n minus 1. So that takes care of the lower bound. Well, most of it. There's a little bit more, but only a little bit, which I won't explain. Okay, and then the upper bound is, in this case, is a rather different story. So the upper bound, so generally speaking, or at a higher level, we also apply this Montiel-Ross argument, which is somewhat similar to the one I just described, a special case of it at least, but with note the Neumann condition now imposed. But there's another important difference, which is that in this case, it's not clear to us anyway how to use the symmetries to do an argument like that, whereas in the Lawson case, Nikos and I were able to do something like that. So instead, we resort to the fact that we know how these are constructed by gluing. And so we're going to partition the surface, but we're not going to partition it in a way that's motivated by the symmetries, but rather in a way that's motivated by the construction. So we cut the surface into pieces which look, say, like the yellow piece, which looks like the tower, right? In this case, I didn't say, but you use a Parker-Shirk tower, or just a Shirk tower with 4. Well, you cut it in half, so there are 2 ends instead of 3. There's no disk in this picture in the middle. Okay, so you have that yellow piece, and you can understand you can study the low spectrum of the tower, and then you have to see what the effect of so you have perturbations because of the interpolation, and then you do an additional perturbation to get minimality to get an exact solution. So you have to estimate, and you have to see what the effect is on the spectrum when you do that, when you consider the Neumann spectrum, and similarly for the catenoids. So you do that, and there's no reason to expect that that's going to give you something optimal, and it doesn't. It does not seem to in this case. But it gives you a bound which seems to be improvement, and this kind of argument actually is enough to get you the equivariant index. Okay, and then as far as I don't know, maybe end with some with a question. So of course there are many questions, but so very recently in August we put on the archive another preprint where we look at another family, now a 2-parameter family, which we construct, and I won't say anything about it really, except that it includes this Fourier-Picard-Solotarev family. I say it includes, that's really conjectural. It's hard to tell when the surfaces you construct by different methods, even when they're both gluing methods, if they're actually the same surfaces or congruent, but I think it's it's extremely likely that they're the same. Anyway, they have a similar description. And we have shown in this later work by similar methods, although there are some novelties, we have shown that the index is at least 2n. Well, actually, this lower bound comes from essentially the symmetry argument, so that aspect is not different. The index is at least 2n. It's conjectured to be sharp. That corresponds to the table earlier on. And the question is, well, is it actually sharp? So we don't have a proof. So that's something which would be interesting to me. We still don't have the Morse index for any family in the ball. But I'll stop there. Thank you very much.
David. Thank you, David, for your nice talk. Are there questions, comments? Okay, Alessandra.
As a point when you show the result, it appears a very full convergence. Can you go back to the slide?
Yeah, sure. Yeah, there may have been a couple of points, but yes. Did it show up again here? No. Okay, so this is one instance.
Okay, so my question is, why very-fold convergence? In the sense, it's a genuine very-fold convergence. You cannot get more, or there is a reason why very-fold convergence.
Oh, why we say verifold? Well, I mean, why verifold? You could, I guess, you could describe what's important. So, for the construction, it's not important actually, but this is a nice way to communicate what's happening.
Okay, because you have a very strong construction with
P. Yeah, so you can describe it in other ways in CK convergence in neighborhoods. Yeah.
Okay.
Yeah, and that's how we work with it. We don't work with that perspective.
Yes, because you have, okay.
Yeah.
Okay. Okay. Are there other comments? Okay, so
I have more philosophical question now.
Great.
So please don't take this as a critique, because I really like the results.
Okay.
So the question is where this business is going in general.
Yeah.
So because you have show the table at the very beginning with a lot of example.
Yeah.
But at the moment it's somehow clear that you cannot cover the entire table. Or
yeah. No, it's not clear to me certainly that you can. So yeah, I mean, right. I raised a lot of questions and went only a little bit with each one, but yeah. So that's a huge question, which topological types are realized. Yeah, the constructions that we're doing here, they're not. I mean, it's not clear to me anyway that there's some kind of program from these constructions to get there. You see something interesting for us. We saw something which seemed interesting to us, and you can do the construction and you can say something new. But I wouldn't say that this is sort of making our way systematically to completing the table. Yeah, I just raised that as an interesting question.
And which kind of general question you think you can answer with the program? If there are any, it's already super good having great examples.
Yeah, no, I mean, I would like to have. I mean, I'm not really setting my sights on that. I would like to have index computation. I mean, I would like, so the reason, yeah, I mean, to focus on the index, the reason I would like to be able to compute the index for more examples is so you can have a chance of saying something interesting about classification. If you don't even know the values, then it's hard. But yeah, I mean, I think so many of these examples, there's some tension because for these constructions, the gluing constructions, you're really just existence only for a large topological type, and you'd really like to. I think you want to look probably at the lower index. So there's some tension there, but I think if you have more examples where you actually have the value, that would be interesting to be able to say more about the relation between the topology generally, or even asymptotic questions are interesting. So there's a lot we don't know, and it's just nice to get more information. Yeah.
Okay, I have a curiosity, but tell me if the question would take too long, okay? Because it may bore the audience.
Okay.
Could you come back at sort of the beginning when you stated those estimates on the index, the very first ones you showed?
Oh, the computation, yeah.
Yes, because you said that the proof used a decomposition and the Dirichlet problems, right?
Yeah.
Okay, I was just curious. Yeah, this one. I was just curious how those Dirichlet problem gives you information on the index, because I don't know anything at all about this. I can't see how you work out this thing.
Yeah, I tried. So that was
in the next
well, I was trying at the very end.
Okay, so
maybe it was confusing to
okay, so what you said at the very end was linked also with that procedure there.
I tried to outline, at least in kind of a special case with this picture, to give some indication of what the general argument is. So the idea is you do this. The argument is very similar to these proofs that I've seen of the current nodal domain theorem, but you don't. I don't know if that's something that that helps or not. But maybe some people it gives a sense of the argument. So, the idea, as I tried to outline here, is basically very basically, you have eigenfunctions on the subdomains with Dirichlet data. Except, maybe there's additional boundary in the free boundary case, and you don't do anything with that. You can extend those eigenfunctions trivially, so just extend them by 0 to the whole thing, and you get test functions. So I mean, that's just to give some indication of how you could get a test function with. So if you you look at all the eigenfunctions which give you the index and the nullity, so eigenfunctions of eigenvalue less than or equal to 0 on the subdomain, and you do extension by 0. And the test functions you get in that way, the Rayleigh quotient is going to be less than or equal to 0, and so you can use these test functions to say something about the index of the whole surface. I mean, that's the basic principle. I tried to give a slightly clear idea in this picture, but at the end, but that's the idea.
Okay, thank you. Okay, if there are no other questions or remarks, we thank David again.
Thank you.
Okay, it's time to go on with this morning session. The next speaker is Michele Caselli, who's talking about, let me check here, asymptotics of the fractional perimeter and existence of bounded harmonic functions on Riemannian manifolds. I forgot to say that Michele is working here from Scuola Normale, so he is one of the home speaker, of this workshop. So please, Michele, you can start.
Thank you. Can you hear me? Okay. So first, I'm very thankful to the organizers, for giving me the chance to talk here. Also because, so this paper is a bit of a story. So, now I have the impression the title is very misleading, on what we find. Now, the version that now is on archive has very different things from the first version. So I'm happy to give an overview of what we find. So I will go on. So first, this is, I can just say it by words. This is a joint work with Luca Gennaioli from Sissa in Trieste. And I will go on more or less how we found our results. Okay, so I will do a bit of history of the past, which are 2 results on the asymptotics of the fractional perimeter as S goes to 0. And then I will explain what we find during the journey. Okay, so first, in the first work regarding the asymptotics of the fractional perimeter for S extends to 0 is a result by Serena Di Piero, Figalli, Palatucci, Valdinoci, 2014, 13, I believe. So they study, and also don't get scared, because if you are afraid of fractional stuff, because we will forget fractional perimeters in 5 minutes. Okay, so resist for 5 minutes, and then you won't hear the word fractional perimeter almost never again for 1 hour. They study the limit for the fractional parameter that tends to 0. This is just the correct normalization constant. The S perimeter of a set in a subset. Okay, so this is, if you want, the fractional perimeter is defined as the squared HS over 2 seminorm in omega, which I can write you what it is, but for today is not very much important. So this is Rn times Rn minus omega complement times omega complement. And then here you have the classical Gagliardo seminorm. K of y squared over x minus y n plus s dx dy. So I think that for today, the most like enlightening way to think about fractional subole spaces is really as interpolation spaces. So think of HS of omega as interpolation between L2 of omega and H1 of omega. So these are like intermediate spaces between these two. And we are interested in, this is like, you can imagine here the fractional parameter S living from 0 to 1, okay? So for S that tends to 0, you would imagine that this in some sense tends to L2, okay, as a space, and also that the seminorm does. But this is like very much not true, and is what like the thing from which our study starts, let's say, because you would expect, oh, by the way, like this is formal, like you can define the fractional subole spaces as interpolation spaces, like with real interpolation theory. It's not just abstract nonsense, okay? You would expect that the, how did I write? Okay, that this, the S perimeter of a set in omega, and I can write again what it is, S over 2 the seminorm, HS over 2 of omega. Like if everything goes well, right? So if this space tends to L2, this would tend to, okay, forget about the normalization constant. This is, in some sense, is inside. You can imagine this being inside the kernel to make this something that has mass uniformly bounded, that tends to a delta in some sense. You would like this to tend to the L2 norm of chi of E intersect omega squared, because I put the square, and this is the volume of E intersect omega. Okay, so the first guess would be this, right? Okay, so note, this is false. This is false. But very, very much false. Like, but in some sense, it's false for two different reasons. So, for two reasons, at least, or let's say I have in mind two reasons, for two reasons. And here we will distinguish two cases. Yes? 0, sorry, always. I should have written it. Okay, there is written. So every limit in S that I take today is for S that goes to 0. Okay, thank you. And so one of the reason is, okay, so you can see this. There is another result. This is not the only result in literature for the asymptotics of the fractional perimeter, is by Carbotti, Cito, Lamanna, and Pallara in 22, so like 1 year ago. So in 22, let me write Carbotti, Cito, Lamanna, Pallara. Find the asymptotics. Find the asymptotics. The asymptotics. Asymptotics on the Gaussian space. Gaussian space, which is the metric measure space Rn, the standard metric, delta, and then a measure, which is like a Gaussian with the correct normalization constant. And the limit is different from this, and the limit is different. So two things. First, and the limit is different from this. So like it's not trivially the L2 norm. And it's also different from what they find in Rn. This, sorry, I should have written the they study in Rn. So this is flat Rn, okay? So these are the only, is different from Di Piero, Figalli, Palatucci, Valdinoci, and also from just the volume, and from E intersect omega. And these are essentially the two reasons why. Now I will explain it more in details, and this is where we get to what, like the work with Luca. So, okay, let's first say a few words about these two results. These two results are, I think they're very nice, but they share a common feature, which is these are basically the only two spaces, Rn and the Gaussian space, where you know explicitly the form of the heat kernel, right? So they take the explicit form of the fractional perimeter and they do the computation. But so we try to fill the gap like of everything in between, basically. So we studied these asymptotics or Riemannian manifolds, every complete Riemannian manifolds. But before, there is another thing to say, which will be probably the most important. So for the Gaussian space, the limit always exists. The limit okay, what is this? S tends to 0 plus of S over 2 S perimeter of E in omega always exist. Okay, so they don't have restrictions. Okay, always in the sense, take a set E that is decent. Okay, say smooth boundary, the limit always exists. On Rn, this is not true. On Rn, this is not true. Not true. And a counterexample is in Di Piero, Figalli, Palatucci, and Valdinoci, but the reason is, in some sense, is very simple, because the limit also depends, and this is even for bounded omega. So take a bounded, so I talk about the localized perimeter. Okay, so this is what, if you send S to 1 and not to 0, would tend to the perimeter of E in omega. Okay, so this is the localized form of the fractional perimeter. So even for omega bounded, the limit depends on the behavior of E at infinity, on the behavior of E near infinity. Yes. Yeah, sure. Yeah. Sure. Yeah. Yeah. Yeah, it does. Yeah. 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 Yes. No, sorry, can you repeat? Yeah. Okay. Yeah. 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 Sure. Yeah. No, pointwise limit. Yeah. Yeah. Sure. I mean, you need like a normalization constant to. I mean, you have to multiply by like 1/2 minus S, and then you get the perimeter, right? Out of what? Like for S that tends to what? Sorry. Yeah. Yeah. Perfect. Okay. Yeah. No, it's not. Like in some sense, to me, it's closer to like BV or like finite perimeter sets than H1/2. No, it's more complicated to 1/2 in my in my view. No, 1/2 is really the critical one, right? Because this is the threshold. The threshold. Okay. Like where you take characteristic functions, they are in HS for every S strictly less than 1/2, but they're not in H1/2, and this is the first one. So it's like that. Okay. Yeah. Okay. Yeah. Yes. Yes, it will. No, don't worry. Yeah. 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 I mean, I don't know if this answers your question, but like to obtain this, so you have to trap like the point is there are sets that have infinite fractional perimeter for every S. Okay, so like to get this, you have to trap your set. This I was a bit sloppy. I was a bit sloppy, but you have to say, okay, take a set E that is in HS0 for some S0, and then you send S to 0. So I always trap the sets to be in some fractional subole spaces, and then I send S to 0. Yeah, if you want only the union of a neighborhood, right? Of a neighborhood, like of the origin of S close to 0, right? But yeah. Yeah, but how do you fix this issue that there are sets that have infinite fractional perimeter for every S? Like, okay, yeah, I don't know. I don't know how you fix this. Like, this is no, we're doing the pointwise limit. Yeah. Okay, yeah, no, don't worry. Thank you. But we can talk about this later if you. I'm happy to. No worries. So okay, we were talking about like how this limit, even the localized one, depends on the behavior of E near infinity. Even if omega, you can take the ball of radius 1. Okay, the ball of radius 1 is, who cares? And how it does so? So in always Di Piero Figalli, Palatucci, and Baldinoci, and this is where we start like forgetting about fractional perimeters. They find the result in terms of this measure, and I will say many things about this measure. So this is like a measure, so it's a subset of Rn, okay, as the limit as S tends to 0 plus of S over 2, the integral on Rn minus the ball of radius R as 0, 1 over x to the n plus s. No, this is E, sorry, if not, E doesn't appear on the right-hand side. This would be a bit bizarre. Dx. Okay, so, and this is the point. This need not to exist, okay, for every set E. And I will give you like a glimpse of what this is just by pictures. I think it's more, I mean, it's clearer. So first, you can prove if this exists for some R is independent of R. Okay, so the ball of radius R is only needed like to take the origin out of this kernel. But if you like compute this in an annuli of any two radiuses, this goes to 0. Okay, so this is independent of R, or you can see is really a quantity of E at infinity, right? Is independent of R, and this already implies, for example, that E bounded, take R big enough so that this is empty, right? And this is 0. E bounded, alpha of E is 0. Okay, but the interesting part is like when alpha is not 0. And this is somewhat measuring, like, this is what they say in their paper. And from what me and Luca do, you will see it's only 50% correct. Is a measure on how conical E is near infinity. So if you plug in a cone, E is really a cone in Rn, then you get the measure of the intersection of E to Sn minus 1. So E cone implies alpha of E equals Hn minus 1 of E intersect Sn minus 1. Okay. Also is invariant by rescalings. So alpha of E is equal to alpha of lambda E for every lambda. And also basically, like, if you take the combination of these two, this I will just say in words, if E has conical blowdown in L1 lock, then the same holds with the limit cone. Okay. So it really looks like, and then you can also see why it need not to exist, right? So why can alpha not exist? Again, I will do a proof by picture. So you just take, you know, it exists for cones. You just take a set that populate between two different cones at different scales, right? So you start with some cone, then you zoom out and you interpolate between a different cone, then you zoom out again and you go back to the first cone, right? And this alpha, this is the set E, and this alpha has two different subsequences. Like this has two different conical blowdowns, right? On two different subsequences in L1 lock, and so the limit does not exist. Okay. So like this issue of the limit existing or not is real, is not like a feature of the smooth boundary or not smooth boundary, right? Okay, and this is where things get very interesting for me, because when you try to study this on manifolds, I think it gives a very enlightening point of view. So again, if you have a question, please. Sorry? Yeah. I mean, if you want, what do you mean by intuitive? Define intuitive. Like for me, so for me, yes, because in some sense, this is like for S that stands to 0, more or less, this kernel is tending to a delta at infinity, right? Because like it's going to 0 pointwise everywhere, and it's concentrating all the mass at infinity. And so really, you don't see anything like close to any bounded set. Like you only see like things close to infinity. You only like, you are in Rn, yeah. No, okay, I think this is my answer. Okay. Okay, so I was interested in the asymptotics just because I found very weird that the only two result existing were the only two spaces where you know the explicit form of the heat kernel. So I just thought like there should be a proof much more structural that works on every like manifold, metric measure, whatever. Okay. I mean, for the same reason, people care about any asymptotics. I mean, it's a limit behavior of like, why would you care? I don't know, about the asymptotics as n tends to 1/2 in the same way, right? Is there? yeah, so like for me, the interest is more, and we are getting to it now, like to see what this kind of stuff does on really geometric ambient spaces. So like okay, this is already somewhat interesting on Rn, but like for me, it's like it's interesting when you can recast all these kind of questions just in terms of the heat kernel of the manifold, let's say, and you will see that this is very much related to real stuff in geometric analysis, like not. So if you want, at the beginning, I see no particular motivation, but in some sense, we were somewhat lucky. I think in the journey we found very interesting like links with other stuff. Okay, but I'm gonna talk about it now. So if so on Rn, this is more or less everything. So you know that if this limit exists, they find the limit. I didn't even write down what the limit is, but whatever. And there are sets for which it doesn't exist. Okay, so it becomes very interesting when you try to do this on a Riemannian manifold. So from now on, MG is any complete Riemannian manifold, any complete. So just to be clear, like really any complete. So I will never assume something about curvature or whatever. So our result is very general, which is both a pro and a con, because like it also treats manifold that are very pathological. Okay, but I just assume any complete Riemannian manifold. So you can note this. Note that you can rewrite basically that quantity. So if you want C of S n plus S, this is 1 over gamma. I think this is minus S over 2, I believe. The integral from 0 to infinity of the heat kernel of Rn at x0t dt t over 1 plus S. Okay, so note that this is true. So this is where, in some sense, this was true before this. Like people in Rn just write this because they have this formula, but this is the correct definition of the kernel. Okay, and so C of S behave like S over 2 as S tends to 0. So on M, the first naive thing, which is okay, is the correct one. On M, we would define the S kernel, say, from between 2 points, X and Y. This is the definition. And 1 over gamma to the minus S over 2, the integral between 0 and infinity of the heat kernel, XYT, the T over 1, T1 plus S. Okay. So you define this kernel, and note that I have put a constant somewhat inside. So when I will take limits, I will not write the S over 2 in front, because the S over 2 is like in this gamma. This you need the absolute value, I believe. But not because the limit is different. I've just put the constant inside. So, and if you ask the same, so let me see. On M, and we start, and we would like to study. Okay, let me write this on the other board because this is very important. This quantity, which I will call theta of E of PR, which is defined as the limit as S tends to 0 plus of, you try to do the same, but since on any manifold you don't have an origin, right? You just put the kernel X, P, the volume X on E minus a ball BR of P. Okay. So you just try to do the same. You take away the singularity, right? And you try to compute the same limit. And you can ask if this is independent or not of R and P. And okay, so let me do things in order. So note, this is independent of R, but it's much harder to show independent of R. So you need basically two ingredients. the proof is not very hard once you have these two ingredients. So, okay, let me do also this. Let me assume for a while that the volume of M is infinity. That the volume of M is infinity. Volume of M is infinity. This is like to stick to the case as in Rn, right? Because on the other hand, the Gaussian space has volume 1, as finite volume. And what like me and Luca find is that the two different behaviors, Rn and the Gaussian space, are in some sense the only two possible, only based on the fact infinite volume or finite volume. Okay, so now I go on, but always infinite volume Riemannian manifolds. Okay. So the proof is not hard when you have two ingredients. So you know that the heat kernel T tends to 0 as T tends to infinity. So this is proved in our paper. We have the impression experts already, like experts knew this, but I think this is not written anywhere on any complete manifold in infinite volume, right? So if you add any other assumption, like curvature assumption or whatever, this is easier. But we do this by spectral theory, like in our paper, but you don't know that the spectrum is discrete. So you have to be a bit careful with the spectral measure, but this is true. So any manifold with infinite volume has the int kernel that goes to 0 pointwise, okay? And then locally everything, right? By elliptic PDEs and stuff. And another ingredient, which is a local estimate, okay, let's say how much time do I have? No, okay, I'm fine. And this, BR of P, H, M of XPT dvx less or equal than e to the minus c over t. And this looks very easy, but it's not so easy because we need this on every complete Riemannian manifold, right? And also we need the constant to be local, okay? Because the curvature of my manifold could do whatever at infinity. And indeed, we will see an example of a very ill-behaved manifold. So we need here a local constant on BR. And this is taken from another work that I have with Joachim Serra and Eric Florit, where we prove this kind of heat kernel estimates based only on local quantities, even if this is an integral on the exterior. Okay, so once you have this, is not very hard, the proof. So no dependence on R. So we write just theta of E B. Okay, no dependence on R, so this is a function of the point. Okay. And again, this is a function of the point that in Rn, if it exists, it's constant. Okay. It does. Oh, maybe this was important, but I haven't said it earlier. Oh no, okay, because okay. Yes, in some sense, the origin has no role in Rn. So you take out every set that contains the origin, that takes out the singularity of this at 0, and the limit is the same. So you would expect that in well-behaved manifold, if this exists, is independent of the point. Okay, is a well-defined quantity, independent of like where you put the singularity. But this is not true, and this is the main point of. So this is a funny story because in the first version of the paper, what I'm about to say was written like in a remark at page 35 before Alessandra told us like that this probably had to be the main theorem. so now it's the main theorem. Thank you, Alessandra. So so the question, but is theta independent of P? Of P? And the answer is no. No, but like by far on general Riemannian manifolds. And so let us first see what is theta for the whole M. So instead of putting, because this has the issue that you can have a set E for which it doesn't exist, right? But if I put E equals to the whole M, this always exists. Let us see first theta of M, okay? And so in Rn, this is 1. This is identically 1. So first, what we prove with Luca is the following. So theorem. And this is me and Luca Caselli, is that theta of M is identically 1 as a function of P, if and only if the manifold is stochastically complete. This is not too much surprising. M is stochastically complete, and I'll tell you what this means. Complete, i.e. The integral of the entire M of the heat kernel dvx is always 1 for every t. So there is no mass escape in finite time. Okay. So if the manifold is stochastically complete, theta of M is identically 1. But if not, then theta does depend on the point, indeed. And a second theorem that we find, Caselli is theta of M. So first, for the normalization constants that I put, theta has always values between 0 and 1. Okay, so if you look at the quantity by Di Piero Figalli, Palatucci, and Baldinoci, it had value between 0 and the measure of Sn minus 1, right? Because it was a measure, if you look at it with cones, it's a measure of how conical at infinity it is. We have put constants so that this is always between 0 and 1. Okay, just not to be confusing about this. So our result is that theta is always harmonic and bounded, as I say, and with values in 0, 1. Values in 0, 1. Okay, included, if you want. And so this is where there is like a big drift in these results, because you can see that bounded harmonic functions or Riemannian manifolds can exist, like non-constant bounded harmonic functions. So this is to say, basically, if we are on a Riemannian manifold where bounded harmonic functions are constant, we can prove the same result as in Rn. So we can do the proof as in Rn. So this I already wrote. So okay, let me define this precisely. So n can be, and I can be different from a constant. So from now on, we talk a bit about bounded harmonic function of manifolds. Let me define what I will call the L infinity Liouville property, which is let's say, it's not only me. We say M has the L infinity Liouville property if, let's say, U bounded harmonic implies U constant. So just as a disclaimer, there are plenty of manifolds that don't have the L infinity Liouville property. I wanted also to show you an example. So let me do a small digression. Note, how can the L infinity Liouville property fail? How can L infinity Liouville property fail? So for reasons regarding time, I will again do a proof by picture, more or less. So I think the easiest example, so there are plenty of examples. Like, for example, in the hyperbolic space is not true by far. So the dimension of the space of bounded harmonic function is infinity on the hyperbolic space. But I think the easiest example is more or less this. You take 2 copies of Rn, and you attach an egg. Okay. And for n greater or equal than 3, this does not, I will tell you why in a moment. This does not have the L infinity reveal property, not have the L infinity reveal property. And there is a sort of easy way to construct a bounded and non-constant bounded harmonic function here, which is you do this. Say that the situation is symmetric. So this is the origin of both Rn, the neck is radially symmetric or whatever. You take the middle curve of the neck. Then say take the bottom part and I take a ball of radius r. Okay. And I solve this problem. I solve Laplacian of u. Okay, let me just indicate the dependence on r. Laplacian on u r equals 0 in what I will call A, and A is this region. Okay, so the region of the ball plus the neck to gamma. Okay. Then UR equals 0 on the boundary of BR, the one below, and UR equal 1/2 on gamma. So you solve this Dirichlet problem. Okay. And you can imagine like on top, I will put 1 minus u. Okay. As you send R to infinity, you have that a subsequence converges in C2 lock, whatever you want. But the important part is as R tends to infinity, this converges to an harmonic function between 0 and 1 on the wall M. But you have to know this is not constant. And as R tends to infinity, for n equals 2, you converge to u infinity equal 1/2. Okay, because like the fundamental solution is logarithmic, so it's not growing fast enough, it's not, sorry, decaying fast enough to convert to something non-trivial. So you send R to infinity, you convert to 1/2 everywhere. But for n greater or equal than 3, you convert to a bounded harmonic function that goes to 1 on this Rn, goes to 0 on this Rn, and does 1/2 here. Okay. And this is very much like, this example is very much almost everything that can go wrong, because there is a result by Alexander Grigoryan in 95 that we can also reprove with with our machinery of this kind of existence of harmonic functions that I will tell you. So there is a result by Grigoryan in 95 that tells you that let me say, the dimension of the space, this is the space of bounded harmonic functions on M, okay? The dimension of the space of the bounded harmonic functions on M is the maximum number of this joint massive, I will tell you what this means, massive sets you can put on M. So I don't have much time, so I will have to be a bit sloppy, but a massive set is like a set that is, with respect to probability, very large in the sense that you can think, it's not completely true, but you can think that a massive set E is more or less a set that has the following property. So the probability that a Brownian motion that starts from X is in E, so you start from the set, the probability that a Brownian motion starting from the set at time t always lies in E, in E for every time positive is positive. Okay, and this is why it's important to say probabilistically, because I think it's a bit counterintuitive at first that, for example, on Rn, half spaces are not massive, because you can decompose the Brownian motion in the parallel part and the orthogonal part, and the part orthogonal to the half space is a standard Brownian motion, so wherever you start, it will go in and out infinitely many times. And here you can also see why for n greater or equal than 3 only this is true? Because the Brownian motion for n greater or equal than 3 is not recurrent. So if you start away from, and this is where the neck is attached, right? If you start away from the ball centered at the origin, any compact sets, with positive probability, you do not visit this again. And so these two copies of Rn are really like detached from each other with positive probability, okay? And we can more or less reprove this theorem because we have a machinery to construct bounded harmonic function and Riemannian manifold. I think I haven't told you yet, but okay, I will leave the definition of theta v. Okay, let me erase R, right? I will put 1 because we know is independent of the radius, 1. So another theorem that we prove, I mean another, in some sense, I already told you a special case. I told you that theta of m is an harmonic function, but what we prove is that if theta of v of p exists for some p in m, okay, hence any. This is kind of obvious if you think about probability, not so obvious in my view if you think about it as a PDE or as a limit, and hence any, then theta of v is an harmonic function. Okay, so this like gives you a recipe really to construct bounded harmonic functions on Riemannian manifold in a way that is very structural because it's okay, yeah, I can tell you. Honestly, I don't know if this paper will ever be out. So this the reproving of this theorem by Alexander Grigorian is not done in our paper. We will maybe do this in a future work, but the moral of the story is very easy because once you know this, you just have to prove basically that, let's take the hyperbolic space. This is Hn, where I know that the space of bounded harmonic functions has dimension infinity. On every of these cones, you can take the standard model of the hyperbolic space with the metric in the ball. Every of these is also massive, okay, but has the limit that exists, okay, and is a non-constant bounded harmonic function on the hyperbolic space. And the point is, if you take two disjoint, we can prove this is what is not done in our paper now, but we can do this. You can prove these are independent. So these two harmonic functions, say E1 and E2, we can prove theta of E1 is linearly independent from theta E2. And so like you can reprove that theorem basically with what we do. Okay, you just take the space, you split into like the maximum number of pieces of the cane that you can put, and I have a recipe that gives you that much bounded harmonic functions on them. Okay. Okay. No, okay, I have some time. So there is another reason that for which this theta of m, sorry, of the wall M is very particular. And is the following. So let us look at the, let me be very brief, at the fractional Laplacian. Minus Laplacian 2ds on a Riemannian manifold. Okay. So I don't want to be too precise. There's no reason to. You can really imagine this as like the fractional power S is 0 and 1. This is the fractional power of the operator in the sense of function analysis. Like if you had a bounded linear operator between two Banach spaces, I could give you the formula that that the fractional power satisfies. Okay, or if you want, like, if you decompose these, okay, maybe this is the most clear. So on any m, you can imagine, I will tell you why, like, this is a bit sketchy. You can imagine the fractional Laplacian to really be the integral on the spectrum of minus Laplacian to lambda to the s against the spectral measure. So this is sort of obvious if the spectrum is discrete. You just put the correct power on the eigenvalues and the eigenfunction are orthogonal, whatever. But this is always true. But you have to be careful because different definitions of the fractional Laplacian are not equivalent on general Riemannian manifolds. So what we prove is two things. So again, if M is stochastically complete, then it's more an if and only if, but okay, but let's do this. The spectral fractional Laplacian, so in the sense really of spectral theory, is equal to what I will call the singular integral fractional Laplacian, which is defined as the integral over m of u of x minus u of y k of xy dvy, and where this is the k I have defined integrating the heat kernel. Okay, so on Rn, this is the usual formula that people write for the fractional Laplacian, u of x minus u of y over x minus y to the m plus s dy. Okay, so if the manifold is stochastically complete, these two definitions coincide on functions that are decent, more or less. But if the manifold is not stochastically complete, they do not. But for the asymptotics of the fractional Laplacian, this is really an issue because if you can use like abstract no sense of spectral theory, you can find the limit as s tends to 0 plus of minus the s Laplacian, the spectral one, of u. You can find it by the representation formula, and this basically equals to u minus E0 of u, where E0 is the projector. You would say on the eigenspace relative to lambda equals 0, so on harmonic functions. On harmonic functions. In parentheses, in L2, because we are working in the space of u. And then just like depending on whether any L2 harmonic function on M, so, okay, two things. I think it's attributed to Yau, even if it's not too hard to show that on any complete Riemannian manifold, an L2 harmonic function is constant, okay? And so you have just two possibilities. So if the volume, and this is very consistent with what we found also before, the thing that matters is just volume finite or volume infinite. If the volume is finite, that you have one function in that eigenspace, which is like normalized 1 over the volume to the 1/2, I believe, right? Because you know it's constant, this normalized to have L2 norm equal to 1. And if the volume is infinite, is 0 project on 0. Like it's 0 sense to 0. Because this is the only constant function on M in L2, right? So by spectral theory, you can get this. Again, this is not very, very new at all, but this is the danger. So for various reasons, when you want to treat the fractional perimeter in a Riemannian manifold, in some sense, this is the correct definition. So the perimeter induced by the singular integral, not the one by spectral theory, is correct. And I could give you more details, but for me, the main reason of this is if the manifold is not stochastically complete, this would give a definition of the fractional perimeter that is not invariant under complementation. And the main issue is just because, like, if you take the function 1 and you let it flow with the heat kernel on a manifold that is not stochastically complete, it does not stay is equal to 1, then becomes different from 1. Or if you want that the spectral fractional Laplacian of the function 1 is not 0, okay, in general, but the singular integral fractional Laplacian of the function identical to 1 is 0, okay? So if you want your notion of fractional perimeter to represent a perimeter in any reasonable sense, at least for me, the perimeter of E should be equal to the perimeter of E complement. And so this is the guy that you have to plug in, okay? But this raises the question, but if M is not stochastically complete, then the two definitions do not coincide. And also, not only they do not coincide, so, and you don't have like a spectral theory to help you finding the limit, which is very, it's very handy. Like it's a representation in terms of the eigenvalues. If you send S to 0, like you kill everything apart from the 0, basically. And so if you want to find the limit as S tends to 0 of the singular integral fractional Laplacian, you have to do it by hand. And this is what we do. So have to find the limit as S tends to 0 plus of minus S singular integral of U by hand. And we are able to do so under very general assumption. And basically, the result is the following. Always volume of M is infinity. I'm complete. This is basically the only thing that we assume. Then the limit as S tends to 0 plus of minus the singular integral fractional Laplacian. This is theta of M times U. And this is the theta that I told you before. Okay, so this is consistent because I told you that me and Luca proved that theta is identically 1 if and only if M is stochastically complete. So if M is stochastically complete, this is not there. But we already knew by spectral theory that you tend to identity. You go to the identity. Okay, but this is really controlling like how this operator like bends towards infinity based on how much the manifold is not stochastically complete. Okay, so this is really the error in some sense, because if you do the limit for the spectral fractional Laplacian, you get the identity. But for the singular integral fractional Laplacian, which I told you is the most reasonable one to represent a perimeter, like you converge, you have a bounded harmonic function in front. And then there is this very, okay, yeah, I have 3 minutes, so this is very nice. And then you can wonder, okay, but how bad can this thing go? Like, and we found, no, it's not that we found, but there is a Riemannian manifold that was constructed by Pinchover, built by Pinchover. In some sense, for different reasons. So he was trying to find a Riemannian manifold that has the L infinity Liouville property, but is not stochastically complete. Okay. And this shows, since the hyperbolic space does the opposite, the hyperbolic space is stochastically complete, but does not have the L infinity Liouville property. This shows that these two properties are orthogonal, are independent. But we note that on this Riemannian manifold, actually we can prove, but this is very simple. All the work was done by Pinchover, to be honest. Has that theta of m is identically 0. So the mass escapes so fast, like is so much stochastically incomplete that at every positive time, in some sense, everything disappears. And so this to me is quite curious to see that then there exist Riemannian manifolds where the asymptotic, if you want, the asymptotics of the fractional perimeter, which I told you this should tend somewhat to the volume. This is 0. Like for every set, for every E, for every omega, for every whatever is 0. Okay. And okay, and this is nice. This is just a random. And I will finish by giving somewhat an open question that me and Luca could not give an answer to, related to the L infinity Liouville property. So I told you that theta of V is always harmonic when it exists. So we know the implication. So if the L infinity Liouville property holds, then theta of V is constant whenever it exists. Whenever it exists. And the question we couldn't give an answer to is that if the opposite is true. So, but this is very tricky because, let me state it and then I will tell you a few words. Say M has the following property. So for every E for which theta of V exists, theta of V is constant. The question is that, is it true that M has the infinity Liouville property? Okay. And this is like to say, I don't know the answer. Maybe I have one of the two things that I believe more, but is asking whether, in some sense, so take characteristic functions, okay, of sets, and run the heat equation till time equal infinity, okay. In the limit, you will catch an harmonic function between 0 and 1, right, by the maximum principle. And this question is basically asking if the set of sets E for which theta of E exists is enough to catch all the harmonic functions, okay? Because you know that is constant whenever it exists, but you are somewhat restricting the family of initial datums that you start from, right? And so I don't know, I don't think this is interesting for something like else in mathematics. It's just, I'm interested in this. And if someone knows the answer, I'm happy to hear it. And I'm done, I believe. Okay, thank you.
Thank you, Michele, for your talk. Are there questions or remarks? Okay. I actually had a curiosity when you first mentioned the stochastic incompleteness, because
Yes.
I once came across this notion and I never studied it, but it seemed to me it's got some connection with the existence of the positive Green's function, something like one implies the other.
Wait.
Because I sort of remember that it's something that was related.
No, yes, I think it's an if and only if. Like, so if you are not stochastically complete, I think that the construction, in some sense, the classical construction of the Green function gives you infinity. No, it doesn't. If you are not stochastically.
If I'm not.
Yeah. And if you are stochastically, but this is, the Green function, if it exists.
Positive, okay.
See, yeah, so the positive minimal, all the whatever, G of xy is this, if it exists, xyt dt. And you can just say like that since this satisfies the heat equation, this satisfies that the Laplacian is a delta at y or whatever. And so, yeah, this is really related, like the convergence of this is really related. No, wait, this has, no, okay, this is correct. The convergence of this is related to the behavior of the heat kernel, like at every time, not only at 0, at infinity, but this is stochastical completeness, like matters with stochastical completeness.
Okay, so you are sort of saying that, okay, that
That's what you say is true.
if and only if you have a positive Green's function.
Yes.
Okay, fine. Okay, because this is a very studied assumption in Riemannian geometry.
Yeah, yeah, I agree.
It's non-parabolic. It's called
and also
non-parabolicity.
exactly when you are not stochastically complete, like the literature is almost non-existent because nothing works. Like not nothing works, but it's very bad for things related to the heat kernel. And
yeah,
the
for the heat kernel, it's very bad.
But also for the green function, right? Because they're more or less the same thing. So yeah.
Okay. Thank you. Okay. And if there are no other questions or remarks, we thank Michele again. Grazie.
Pleasure to meet you. Introduce the next speaker, who is Liangjun Weng from University of Rome Tor Vergata. And he is going to talk about Alexandrov-Fenchel inequality for convex hypersurfaces with capillary boundary in a ball. So please start.
Okay. Thanks, Lucas' introduction. And also I want to thank all the organizers for the invitation. And it's my great honor to give a talk here. So I will talk about the Alexandrov-Fenchel type inequality for the convex hypersurfaces with boundary in a ball. So this is a joint work with Professor Guofang Wang from Uni Freiburg, and also Chao Xia from the Xiamen University in China. Here's the structure of the talk. So the first part is a review of the classical asymmetric problem, and then the second part is the high order version of the asymmetric problem, the so-called Alexandrov-Fenchel inequality, and the last two parts are the corresponding relative version of the first two parts. So here relative means that we consider the hypersurfaces with non-empty boundaries. So the first two parts are about the closed hypersurfaces. Okay, so the asymmetric problem asks the question states that among all closed hypersurfaces in Euclidean space, if they enclose the domain with fixed volume, you ask which one minimize the area. Okay, so in particular, when n equals 1, it is a plane asymmetric problem, also known as the Queen-Diddles problem, which has a very long history. And now the solution is well known and is given by the asymmetric inequality. So if you have a domain omega, bounded domain in Euclidean space, then its volume is controlled by the area. And here the coefficient alpha n is a sharp constant, which means that if equality holds if and only if the domain is a round ball. Okay, and for this, there are many kinds of proofs from different viewpoints. In this talk, I will focus on the math using the geometric curvature flow. So I will just give a quick sketch how to use in the idea of the curvature flow to prove the asymmetric inequality. So roughly speaking, there are two types of such kind of flow. Both of them are volume preserving and area decreasing. And the first one was introduced by the Huisken in 1987. So with the speed function is a normalization of the mean curvature. So you have now you have a term here, non-local term, because it only depends on the time t. So some literature they call it global type volume preserving mean curvature flow. And Huisken proves that if the initial hypersurface is uniform convex, then along this flow it will convergence to your model, the solution of your the minimizer of the asymmetric problem, which is a round sphere. And actually, our work are highly motivated by another type of flow, which introduced by the Pengfei Guan and Junfang Li in 2015. So with the speed function is given by the n is the dimension of the hypersurfaces minus the inner product of the position vector and the unit outward norm times the mean curvature. And one of the benefits of this flow is that you can weak the convexity to the star shape. Okay, star shape means that the hypersurfaces is a diffeomorphism to the unit sphere. And Guan and Li prove that if the initial hypersurfaces is star shape, then along this flow, it will converge to your model. Your model is again the round ball, the round sphere. Okay, so both of these types of maybe before that I should back to the inequality. So this inequality, we have a power here, which means that it is a scaling invariant. So for example, we want to prove this inequality, and now we have two quantities. One is area and another is volume. Since it is a scaling invariant, so a very naive idea that we fixed one of the quantities and we just need to compare another quantity with your model. So the idea, this idea will be also used in the higher order case. So for example, you can fix, so by scaling, you can fix the volume equals to your model case. Then this inequality reduced to your asymmetric inequality. Then is equivalent to, you just need to compare the area with your model. Your model now is the unit sphere. Okay, so for the flow method, using the curvature flow method, the idea is that we want to construct a flow which preserves the volume and the monotone decreasing the area, since you have this sign. And if you can show that, for example, this is for example is your flow hypersurfaces, and you can show, if you can show that when t goes to infinity and it converges to your model now is the sphere, for instance. Okay, and from initial you start, and along these procedures, the volume is always preserved for any t, and your area is monotone decreasing. So initial is bigger, and your model is the unit sphere. Okay, so roughly speaking, there are just two steps. Step one, you have the monotonicity, and step two, if you can show, step two maybe right in this way. So here is your step two. You show that the convergence of your flow to your model case, then you are done. Okay, so a very natural idea. So there are two types of flows. So let's see why they are volume preserving and area decreasing. So the first type of flow is by Huysken. So if you take the normalization of the classical mean curvature flow with this phi t, and if you want it is volume preserving, you just take the first variational formula of the volume, and it is the integral of the speed function. And if it equals to 0, you have to choose the phi t in this way, the average of the total mean curvature. Okay, so it's a very natural normalization. And the next is to show that it is area decreasing. So you take the first variation formula of the area. It is the integral of the speed function times the mean curvature. And by some simple manipulation, you can have like a very complete square form of the integral function. So it is monotone decreasing the area. Okay. But our, as I said, we are largely motivated by another type of flow, the local type, since the speed function now is defined pointwise. So to see it is volume preserving, a key observation is that this speed function has something like the divergence structure. It is the Laplacian of the square norm of the position vector. Here take the Laplacian with respect to the induced metric. Okay, then you take the Laplacian, it is exactly your speed function. Okay, so then you again using the first variation formula of the volume, and it is integral of the speed function. And now your speed function has a divergence structure. Actually, here is more better. We have the Laplacian. But once you have the divergence structure, it's enough for you. Since the hypersurfaces right now are closed, so using integration by parts, it equals to 0. Okay, so so when you consider the hypersurface with non-empty boundary, you cannot use it automatically because now you will have the boundary integral terms. So this is a subtle point. So when you consider the hypersurfaces with the boundary, we have to make some modify. But now everything is okay because the hypersurface is closed. Okay, so you don't need to worry about the boundary. And also next we show that it is sorry, not me. The Guan and Li show that this is the area is also monotone decreasing along this flow. So, but again, you consider this function, the square norm of the position vector. So this is a very actually very natural and very important test function. You take the covariant derivative with respect to Ej, and then you take the contraction with sigma 2 Ij. Sigma 2 is the 2's second elementary symmetric polynomial function evaluated at the principal curvature, and the sigma 2 Ij is just you taking the partial derivative with respect to the Hij. Hij is the Wiygul tensor. Okay, and one important of this operator it is that it is divergence free, which means that if you take the derivative I and the sigma 2 Ij, and you take the I summation, it was equals to 0. So when you take the derivative with respect to the first term, it vanishes. So you only have the second term. So for the second term, it was the first fundamental form minus the second fundamental form times the position vector. Okay, then the first term you take the contraction with sigma 2 Ij, it gives you the mean curvature, and the second term you take the contraction with sigma 2 Ij, it will gives you the sigma 2. Sigma 2 from the intrinsic point, it will also the scalar curvature, and now you take the integration in both sides. Since the left-hand side has a divergent structure and your hypersurface is closed, so it was equals to 0. Then you get the integral of the mean curvature with relation to the integral of the sigma 2 times the support function. This function also called the support function of the hypersurfaces. Okay. Then you using the first variation formula of the area, it was the integral of the speed function times the mean curvature. And the first term is the integral of the mean curvature. Then you can replace using this identity by the sigma 2 times the support function up to a constant, which only depends on the dimension n. And you can replace this term. And since you all have this common factor, you can take it out. Okay. And inside it was something like the sigma 2 minus the h square up to a constant, and it has you have this complete square form. Okay, since we assume that it is star-shaped, and this condition is actually preserved along this flow. The star-shaped is equivalent to that this support function is positive. So inside your integral function now has a definite sign, so it is less or equal to 0. Then you are done. So this is area. Along this flow, the area is also monotone decreasing. Okay. Yes. Any more questions? So this what I'm going to talk is quite elementary actually about the asymmetric problem. So in case of any questions, you can interrupt me freely. Okay. So it should be accessible actually to even undergraduates, I guess, especially in Pisa. So this is the first step we have the monotonicity of the volume and the area. Next, you need to show that this flow will convergence to your model. Okay, so here is a sketch of the second step. Guan and Li prove that along this flow, it has long time existence and convergence to the model. So first, the star shape ensures that the flow is parabolic. Then you have the short time existence, and you can convert the problem, reduce the problem to a scalar parabolic equation, which you view the hypersurfaces as a graph over the unit sphere. Okay, then you using the maximum principle, you have the C0 estimate by the avoid principle, and you also have the C1 estimate by using the maximum principle. And since it is a divergence type, quasi-linear type parabolic equation, once you have C1, then you have all the high order estimate. So now you have the long time existence, and for the convergence for this flow, you can have like a better C1 estimate. Actually, you can have the exponential gradient estimate. Here, alpha is a universal constant, a positive universal constant. So when t goes to infinity, you can find that the log u will goes to some zero constant. So u will goes to some constant, which means that your limit is just a scaling of the unit sphere. Okay, then you are done. Okay, here. So now we move to the higher order version, the Alexandrov-Fenchel type inequality. So before that, we need to introduce the notation of the convex integrals, which is for now, if you have a convex body omega in Euclidean space, and you define the outer parallel body of omega, omega ipsilon, which is Minkowski sum of omega and the ball with radius ipsilon. Okay, and the convex integrals is defined as the coefficient of the following standard type of formula. Okay, so it's something like you take the Taylor expansion with of the volume of omega ipsilon, then you got a sequence and with coefficient, got a polynomial, and with coefficient is the convex integrals WK. So in particular, when your domain has a smooth boundary, for example, C2, then you can define the principal curvature. Then you can express all the convex integrals as the integral of the normalized case mean curvature. So in particular, W0 is just the volume, and W1 is the area, and W2 is the integral of the mean curvature. And the last one, the Wn+1 is the area of the unit sphere. Okay, so here HK is the to make a normalization of the sigma k. Sigma k is the case elementary symmetric polynomial function which evaluate your principal curvature of your hypersurfaces. So take this normalization when you evaluate on the sphere, HK equals to 1. So this is just a convention to simplify some coefficient. Okay, so the classical asymmetric problem is about ask the relationship between W0 and W1, so the volume and the area. So it's a natural question that for other geometric quantities, for example, W1 and W2, do you have the relationship? Okay, so that is the Alexandrov-Fenchel type inequality, which states that if you can give omega is a convex bounded domain in Euclidean space, then the WL is controlled by the WK up to a constant, up to a coefficient. Here coefficient is a sharp constant, and here the power again is this power is from the scaling. So this inequality is scaling invariant, and with sharp equality holds if and only if the domain is a round ball. So in particular, when k equals 1, L equals to 0 is the asymmetric inequality, and the k equals 2, L equals 1, it is a Minkowski inequality, because now the W2 is the integral of the mean curvature. And when you replace the right-hand side with the L equals to 0, it is the volume. So it was called in some literature the volume Minkowski inequality. While the last one can be implied by if you combine the asymmetric inequality with Minkowski inequality, you can imply the third one. Okay, so here's progress of this inequality. So initially, Alexandrov proved this for the convex case when the domain is convex. And later, McCoy, using the inverse curvature flow, gave a new proof for the convex domain. And Guan and Li in 2009, they proved using the curvature flow for the K convex and the star-shaped domain. Here, K convex means that your principal curvature is located in the so-called the guiding cone. So why we consider we are interested in this condition. So back to your form of your. So now we have the Alexandrov. So I write an equivalent form of this in this way. So you have the WK and integral on the boundary. You have a sharp constant here, HK minus 1, for instance. Up to a power here is maybe I minus K, A minus K plus 1. Okay, so I just neglect the sharp constant here. So you just compare these two quantities. So from the analysis viewpoint, that a natural condition for this, we do not. We hope that the principal curvature is located in the gamma k. Here, the gamma k is all the for the lambda in sigma 1, sigma j is bigger than 0 when for j between 1 and k. So you just need we want to weak the condition from the convexity to it just requires the integral function is positive. So k convex is k. This is equivalent to what I called k convex. If a hypersurface whose principal curvature is located in the gamma k, then we call this hypersurface is k convex, which is weaker when k equals to n. It is the convex condition. So from analysis viewpoint, so people, many mathematicians want to weaken this assumption. So that is Guan and Li has made a very important achievement in this direction, but on the assumption that the hypersurface is star-shaped. So whether one can remove this condition, as far as I know, this is still an open question. And also Alice Zhang and Wang Yi, they prove this for the k plus 1 convex, for the k equals 1 and 2. And Guo Huanqiu, he proves this for when k is big or equal to 3. Also, there are some other, maybe. This is not a complete list of the progress, maybe some other. K convex means the principal curvature of the hypersurface is located in the gamma k. Gamma k is the sigma, all the G's elementary symmetric polynomial function is positive when for G is less or equal to k. So when k equals, sorry, yeah, for the largest k, when k equals to n, it was convex. So when k equals 1, it just is the mean curvature. So sigma 1 is the mean curvature. It was the mean convex. So when k equals n, it is all the principal curvatures are positive for any I between 1 and n dimension. Okay. Thank you for the question. So since Minkowski inequality is like the second very important particular case of the Alexandrov-Fenchel inequality, except the isometric inequality. So there are also many mathematicians working on this particular case of the Alexandrov-Fenchel type inequality. So initially, as I said, it was for convex domain, it was proved, and later Michael Liang Sam for the general domain, but with non-sharp constant, and also Huisken using the weak inverse mean curvature flow for the domain for the outward minimizer set, and Guan and Li for the mean convex again plus the star-shaped condition using the inverse mean curvature flow proved the Minkowski inequality, and Castellion using the optimal transport method prove this for general domain, but again with non-sharp constant. But this constant is very close to the sharp one. And also Augustiniani and Metti and Masiello, they proved this for the new proof for the outward minimizer using different methods, nonlinear potential theory. And Simbrando proves this for general domain, but with non-sharp constant using the so-called Alexandrov-Beckmann-Pusis method. And also Gallardo recently you prove this for the sharp constant for the when your domain is the C1 ipso perturbation of the ball. And also Childish and Ishmael and Thomas, they have some very nice work, which show that give a something like a counter example to show that this inequality could be fail without the convexity assumptions. So also this is not a complete list of the progress. Maybe this is just up to my knowledge. And actually this, but using a very different, not very, but a different method to study this inequality. And has some maybe more works. Maybe I neglect here. I'm sorry. So now let's back to the flow method. So in this talk, I will focus on the using the curvature flow method. So a review of the Guan Li types method. So Guan and Li, they in 2009, they introduced the following type inverse curvature flow with the speed function is hk minus 1 divided by hk. And a key property of this flow is that they observe that we have the monotonicity. That is the scale invariant quantity of the wk plus 1 divided by the wk up to a power is monotone increasing along this flow by the Newton-Maclaurin inequality. And a property of this flow is that the k convexity and the star shape are preserved along this flow. Okay, and for the convergence, so now step 1 we're done. So you have the monotonicity, and step 2, as I said before, so you have this convergence was done by the Hart and independently by the John Arbus in 1919, and they prove that along this flow it will expand into a asymptotic round sphere if the initial hypersurface is k convex and star shaped. Okay, so then combine this, you are done. So Guan and Li, they prove that proved the Alexandrov-Fenchel inequality for the Quatermass integrals holds for the k convex and star shaped domains. So both this condition is weaker than the original assumption, which is convex. Okay. So now we move to our interest, the relative world. So we consider the hypersurfaces with boundary case. So before that, a rough review is that, as you can see that from analysis of geometric aspect, so asymptotic inequality and its higher order version has a long and also very rich history and very recent nice works. So, but the boundary case, the relative counterpart of those geometric has some, as you will see that the boundary could, we will see later, the boundary would create some new phenomena, or yeah. So our goal is to develop the relative geometric inequality. Okay, so now the simple case, the volume and the area is the relative asymptotic problem. So its question is that among all the question stays in the following way. So if you consider the hypersurfaces in the unit ball, and it is splitting your domain into 2 parts, the sigma hat and the sigma tutor. Okay, so the question is parallel to the classical case. You fix the volume and you ask which one minimize the area. Okay, so now we fix the volume of the sigma hat. It was the tau times the volume of the unit ball. If the sigma hat volume is fixed, then you can see that sigma tutor volume is also fixed. Okay, so the question is the same. So you ask which one minimize the area. So a very natural setting for this. So this was well-known. No, I mean, it was solved. So the solution was given by all the free boundary sphere caps or equatorial flat balls. Okay, so this was proved by the Barago, Mazzea, and also independently by the Barkovsky and Spencer. Okay, so when tau equals 1/2, so the solution is the equatorial flat ball. So just next slide. So you get this is your solution, your area minimizer. And if the other case, it was the free boundary sphere caps. So here free boundary means that hypersurfaces intersect with your boundary of the unit ball orthogonal. So this angle here is pi/2, means free boundary. Okay. So actually in Barkovsky and Spencer's paper, they introduced a very more general question for the relative asymptotic problem. So in general, you consider a very not unit ball, but a convex body in Euclidean space, the K, and you find the question is we want to find the area minimizer of your hypersurfaces sigma, and it is splitting your convex body in 2 ways. So the first way, as I said before, you fix the volume of the sigma hat, and they have proposed a second type asymptotic problem. You fix not the volume, but the boundary, area. The sigma hat located on your outside, on your supporting hypersurfaces, and the partial. Now I call this convex body K is you can call it the boundary, the supporting hypersurface located on this part, the area you fixed. Then in the case when your supporting hypersurfaces is a unit sphere, the area minimizer is achieved. The first one is said before, but also the second one. The second one is the flat capillary. Actually, it was a flat capillary balls. But capillary means that boundary of your hypersurfaces intersect with your unit ball at a contact angle theta. So we will see the second case later. And so combine this work. So it's natural that since for the closed case, we have the Alexandrov-Fenchel inequality, and for the relative version, we have the relative isometric inequality. So a natural question is that whether we have the corresponding relative version of the Quermass integrals for the compact hypersurface with non-empty boundaries. And also for if you have the answer for the first question, you ask whether we have the relative version of the Alexandrov-Fenchel inequality. That is also the high order version of the relative isometric inequality. So we give a positive answer to both those two questions. Okay, so now we move to the last part. So here is our setting. So we consider the hypersurfaces with capillary boundary. Here, the capillary boundary means that your hypersurfaces intersect your boundary of the unit ball at a contact angle theta. So I make the convention that the angle is pi minus theta. You can also make it theta just has a minus sign, which just for convenience sake. So here is picture. So mu is the unit outward norm of your hypersurfaces, and any bar is the unit norm of the unit outward norm of the sphere. And this angle is makes the convention that it's pi minus theta. When theta equals pi over 2, it's called free boundary. Okay. And inside now inside your ball, the sigma and the boundary of the unit ball, they include a domain denoted by the sigma hat. Okay. Now sigma hat has two boundaries. One is sigma, another is partial sigma hat, which is located on the sphere. And both those two have surfaces. They have a common boundary. In the blue color, it was the partial sigma. Okay. And usually in some literature, partial sigma hat is called the wetting area or the wetting part of your hypersurfaces. Okay, so we will introduce the relative Quermass integrals for such kind of domains or hypersurfaces with boundary. So before that, a heuristic idea to see a simple case. So now you consider just a two-dimensional case. You consider hypersurfaces, embedded surfaces in the three-dimensional unit ball with capital boundary, and you denote the mu and denote the mu and the mu bar be the conormal unit vector of the partial sigma in sigma, and another one is in the with respect to the partial sigma hat. And for this two conormal, you have the corresponding geodesic curvature, kappa, which are denoted by the kappa g and the kappa hat. And for the from the capillary boundary condition, you have this relationship between these those normals, and you from this you take the derivative, you will get the corresponding geodesic curvature relationship. Okay, so now you're using the Gauss-Bonnet formula for sigma in Euclidean space. Then you get this. So the integral of the Gaussian curvature times plus the integral of the geodesic curvature, you get it equals pi 2 pi. Okay, and you use this relation. You replace the geodesic curvature with respect to the sigma by the with respect to the partial sigma hat, the wetting part on the sphere. The bound sigma partial sigma hat is a domain. Is dimension is n plus 1, and this is two partial sigma hat has two boundaries. One is sigma inside the ball, and another is partial sigma hat on the sphere. Boundary of the sigma. This is the sigma. Sigma is inside the ball, and partial sigma also on the sphere, but it was in three dimension it was just a line. Partial sigma is just a line, a curve. Oh, sorry, a curve. A curve on the two-dimensional sphere, and the sigma is a surface, two dimension and 3 dimension, and again 2 dimension. Partial sigma hat is a domain in S2, if you consider this. Okay. So you for example, you consider the two-dimensional surface case, then it's so sigma 2. In two dimensions, it was the surfaces. Yeah. Sigma height is a domain. Is a domain. Yeah. Yes. Inside. It was a domain. Sorry, the notation may be confused. So sorry. Yeah. And sigma height is a domain. Sorry. Yeah. The height is bigger height, smaller height. Sorry. Yeah. Yeah, the notation is a little bit confused. Sorry. Okay. Oh, okay. So we have arrived here, and now we're using the spherical Gauss-Bonnet formula in on the sphere. Well, for this now partial sigma height is a domain in S2. Okay, so using the spherical Gauss-Bonnet, you have the Gaussian curvature in the sphere. On the sphere, you have the Gaussian curvature equals to 1. So the integral of the Gaussian curvature is the area of the partial sigma height, and plus the boundary term, the integral of the geodesic curvature. Okay, so now next you replace this back to this term. Okay, now you get this form. Okay, so it was the integral of the Gaussian curvature plus some this is the length of the curve, and here is the area. Okay, but this okay, so you can reformulate it in this way. So the integral of the Gaussian curvature plus these two terms is equals to constant, which depends on the contact angle. Okay, so this gives you the idea that if you want to define the high order relative QMS integrals for the hypersurfaces with boundary, there will be some new terms will come out like this. But and as you can see that all these terms are defined on the unit sphere. Okay, so in order to introduce the high dimensional case, we have some preparation work. That is, we will use the spherical QMS integrals, which now you consider a convex body in the unit sphere, and you can define as in the Euclidean space the spherical QMS integrals. The W0 is the volume, and the W1 is the area, and the other WK can be defined in this induction form. So here is WK, and here is WK minus 2. Okay, so in this formula, you can define all the high order spherical QMS integrals for your convex body K in Sn. And so I with this, I mean all the notation here are in the sphere. Okay. So here is we are ready to introduce the QMS integrals for hypersurface with capillary boundary. So the W0 is the volume, and the W1 theta is the area. Here is the area of the sigma. This is the W0 Sn is just the area of the partial sigma height. Now partial sigma height is on the Sn. Okay, so they have the same dimension, the dimension n. And the highest order Wn plus 1 is the integral of the Gaussian curvature. Hn is just the Gaussian curvature, and minus the rest of term. It's a summation of up to a constant. It's the combination, the linear combination of the WL Sn, the spherical QMS integrals. And here is and in the middle we can also define the WK plus 1. The first term is again as the closed case, as the integral of the HK, and you have other terms which only depends on the spherical QMS integrals and the linear combination of them. So in particular, when theta equals pi over 2, which is known as the hypersurfaces with free boundary, and this concept was introduced by the Yulian Xiaoya and Guofang Wang and Chao Xia. Okay, So you can see that when theta equals pi over 2, many terms will be vanished. For example, cosine theta equals to 0, and this term vanish, and there's only one term left when L equals k minus 1, the highest order. Otherwise, when L is less than k minus 1, this term will also vanish. Okay. So in free boundary case, you can simplify. You just have two terms. One term is the classical case, the integral of the HK, and you have the spherical Kerr-Mass integral for the k minus 1. A very good question. I don't know. Yeah, we don't know actually. Yeah, could be. But for the this is in the unit ball case. In another setting, we consider we define the Kerr-Mass integrals in the half space, where you replace the supporting in the half space. We can have such similar Taylor explanation for the relative Kerr-Mass integrals in half space, but not in the. Sorry. Yeah. Yes. In half space with capital boundary, it was true. And for general theta, which is known as capillary boundary by myself and Chao Xia. So in particular, when you consider the surfaces in 2 dimensions, the W you can write them you can write all the terms. The W0 is volume, and W1 is area, and the W2 is the integral of the mean curvature plus 2 terms, and the W3 is the H2 is the Gaussian curvature in this situation in 2 dimensions. H2 is the integral of the Gaussian curvature. And from previous discussion, we know that W3 theta is a constant. Okay, so remember that we have this motivation previous, not motivation, a very simple heuristic idea. We can, so from this, we know that the highest order is a constant. So here, the motivation why we define the relative Kerr-Mass integral in this form. Okay, it was motivated from by the first variation formula. Okay, so now you consider a family of the smooth embedded hypersurfaces sigma t with capital boundary, and you do if the speed function is given by the little f, and you take the first derivative of our relative Kerr-Mass integrals, you get this very nice formula. It was the integral of the HK times the speed function, and the highest order when k equals n plus 1, it was equals to 0. Okay. So the next question is, you have defined the relative Kerr-Mass integrals, then you ask whether you have also the corresponding relative Alexandrov-Fenchel type inequality. And for this question, we have the following results. So when theta is between 0 and pi over 2, the Wk is controlled by the Wn. Wk theta is controlled by Wn theta. Here, the little fk is a strictly increasing function, which is given in this way. When here theta r is your model, the sphere cap with the contact angle theta, and evaluate when you take this evaluate at your relative Kerr-Mass integrals, you get the fk. Okay. And in particular, this inequality is sharp, which means that equality holds if and only if your hypersurfaces is a sphere cap or a flat capillary ball. So when theta equals pi over 2, it was previously result was proved by Yulian Xiaoya and Guofeng Wang and Chao Xia. And also very recently, Hu Wei and Yang and Zhou, they using constrained mean curvature type flow proved the relative Alexandrov-Fenchel inequality for the Wk theta and the W0 theta. So W0 theta is the volume, and the Wk is the integral of the case mean curvature. But the other case is still unknown. So in particular, when in the surfaces case, we have the following type of relative mean curvature inequality. When now you consider the sigma is convex surfaces with capital boundary, capital means the contact angle is theta. In B3, then you have the following type, the Minkowski type inequality, and the mean curvature the integral of the mean curvature plus some lower order term, which only relates to the spherical information of the partial sigma and the partial sigma height. And equality holds if and only if it's a sphere cap or a flat disk with capillary boundary. Okay, so when theta equals pi over 2, you can see that many terms will be vanished. So this vanish, and this also vanish. So here is the idea, the sketch of the idea for the proof. So again, we construct a local type of constrained curvature flow, which is motivated by, as I sketched before, by the Guan and the Li, the idea, the local type constrained curvature flow. And for our flow, it has a monotonicity, which means that the Wn is preserved along this flow, and the Wk is monotone increasing along this flow. And then if you can show that this flow has long-time existence and the convergence to your model now is a sphere cap, then you are done. Okay, so how to define the introduce the flow? So it was motivated by the Minkowski formula. So now you consider a hypersurface, embedded hypersurfaces with capillary boundary in the unit ball. Then we have the following type of Minkowski type formula. Okay, so the x is a position vector, e is some fixed constant unit vector, and mu is a unit norm of sigma, and hk and hk minus 1 is the case normalized mean curvature of the sigma of the hypersurfaces. And here the capital Xe. Capital Xe is defined in this way. Okay, it is a conformal Killing vector field, and and in particular case when k equals 1, it was previous proved by the Wang and Xia, and for k equals 2, it was by myself and Guofang Wang. And actually, the highest order case, the proof is similar with compared with when you have the k equals 1, you have all the highest order. So with this Minkowski formula, you can so another remark is that for a key point for this formula is that we do not have the boundary term. Okay, even though your hypersurface is with boundary, but in this identity, all the integral are inside the hypersurfaces. So this is the key point. So with this, we introduce the following type of inverse curvature flow. So along this flow, we have the monotonicity. The Wn is preserved and Wk is monotone increasing along this flow. It was using the Minkowski formula and the Newton-Maclaurin inequality, and also the first variation formula. So you take the first variation formula of the Wk theta. It was the integral of hk times your speed function. Okay, so now this is your speed function, and when and you use the Newton-Maclaurin inequality for this term, then you get the hk minus 1. Okay, so now this again you back to the Minkowski formula. It was equals to 0. So Wk along this flow, Wk is monotone increasing, and when k equals to n, you find that when k equals to n, this term this will give you automatically the Minkowski formula. So the Wn is preserved along this flow. And to see the long-time existence of this flow, first we need to have the parabolicity of the flow. So in particular, when theta equals pi over 2, it was previous by the Ben Lamta and Yulian Shoya. They prove that if you give a strict convex hypersurfaces with free boundary in the unit ball, then it must lie in the half ball. Okay, so this will give. So you can see when theta equals pi over 2, this term will vanish. So x, the inner product of x times the e is positive. And for our case, for general theta, we have the following proposition. Okay, so we can find some E0 fixed unit constant inside your waiting part area. Okay, and we have the following property holds. So the first one is the inner product of all the position vectors on the hypersurfaces with E0 has a quantified lower bound, positive lower bound. And if you have the first case, you have the second one, and the second one will give you the parabolicity of the flow. So you have once you have the parabolicity, you have the short-term existence, and the positive of the Hn divided by Hn minus 1 implies that the solution is strict convex. And here is theta r is all the sphere cap which intersect inside your ball and intersect your boundary of the unit ball with the contact angle theta. So these are the model. Okay. So and we have the Berry argument. Okay. This will give you the C0 estimate by the maximum principle. Okay. So and for the speed function has a uniform again by the maximum principle. The speed function has a uniform lower bound and upper bound. And for the lower bound, it will also imply that the convexity is preserved along this flow. And combine the convexity and our specific choice of the E0, you can get the C1 estimate. C1 estimate in this setting is equivalent to the uniform lower bound of the support function. Okay, here you can view the capital XE as the play the role as the position vector in the closed situation. So now you if this has a uniform lower bound, positive lower bound, you have the star shape is also preserved along this flow. And since we have the convexity is preserved along this flow, to show all the C2 estimate, you just need if you can, so you compute the evolution of the mean curvature, and you can derive that the mean curvature has a uniform upper bound. Then combined with convexity, you have all the C2 estimate. Okay. So by the then next, if you have a C2 estimate, then you're done. You have all the high order estimate, and also the long time existence. Okay. And for the convergence, in this situation, we need to use the specific monotonicity formula. Okay. So then you will get the combined with the uniform estimate, you will get the convergence to your model case. Okay, so a final remark is that recently Sembrando consider the following type of also you can view as a relative isometric inequality. So if a sigma is a minimum hypersurface with capillary boundary, then its area has a lower bound, a sharp lower bound, and this is equality holds if and only if sigma is a flat capillary ball, which means that it intersects the unit sphere at a constant contact angle. Okay, so if a sigma, actually I write that, but you can also write in this way. So B with the radius square root 1 minus B square in this way. Okay, in A. Okay. So it was equivalent. So compare now. This is your model. Your model is the capillary flat disk. So when, in particular, when theta equals pi over 2, it was free boundary. It was a previous question asked by Richard Shung and solved by Sembrando himself. And after 10 years later, he proved the capillary situation. So now, and in his result, the contact angle could be variable. It could depends on could be variable. Depends on the point of the boundary. So, so it's more general. So here is the solution. So they are all capillary flat disk. Okay. So and a final remark is that Brandel's assumption for is weaker than Berkowski and Spencer, since the stationary point of the area with fixed boundary area must be a minimum hypersurfaces and intersect your boundary of the unit ball at a constant angle. Okay. So maybe I stop here. So, thank you.
Okay, are there questions, remarks, comments?
Back to your, can you please go back to your Alexandrov-Fenchel inequality, please?
This one?
Yeah, exactly.
Okay.
in the classical Alexandrov-Fenchel inequality, you have a rescaling factor.
Yes.
Here, is it encoded in that Fn composed with the Fk to the power -1, or it just solved for a fixed measure?
I don't know, because now in the sphere, we cannot write it explicitly. We denote this by the little Fk, because even for this, in the closed case, when you evaluate the Queen mass integers on the unit ball with radius r, it is a polynomial of the radius. Yeah, but when you consider in the sphere, it was like cannot write it explicitly.
Okay.
Yeah.
Thank you.
Any other questions? No. Okay, maybe I have one. Are there any chance to relax hypotheses like they've done with the classical Alexandrov-Fenchel or not? Not with this.
I don't know.
Okay. No.
It's a good question whether you can using, because I don't know, maybe you can study that.
Okay, maybe later. Okay. Other questions? No. Okay, so please thank again Liangjun for the nice talk.
Thank you.
Okay, maybe we can restart with the last long talk for today. It's a pleasure to introduce Alba Lia Masiello from University of Naples, and she's talk about estimates for Robin p-Laplacian eigenvalues of convex set with prescribed perimeter. Thank you.
Can you hear me? Okay. Today I will try to tell you a story about an optimization problem in which we want to optimize an eigenvalue of a differential operator that I'm going to write you in a second. And then we want to achieve some more information in order to understand if we can characterize better the problem. So I'm telling you what the problem is. We want to study an eigenvalue problem related to a differential operator. And so the differential equation is the following. We are considering, let's say, an open set omega. And on omega, we want to study the eigenvalue of the p-Laplacian. Okay, that is a nonlinear differential operator defined as the divergence of this vector field. Okay, this is exactly a nonlinear generalization of the Laplacian. And on the boundary of omega, we want to prescribe some nonlinear Robin boundary condition. That's why the eigenvalue that I wrote here depends on two parameters. The first one, you might imagine that is the P of the p-Laplacian. And the second one is the one that describes the Robin boundary condition that are the following. Gradient of u to the power p minus 2 times the normal derivative of u. So here we have the exterior normal to the boundary of omega plus the parameter beta times u to the power p minus 2 u equals to 0. In all of this talk, the nonlinearity p will be chosen to be greater than 1. The set omega will be open, and the parameter beta will be allowed to vary in R. I don't know if you ever seen the Robin boundary condition. Very often when you talk about eigenvalues, also about a Poisson equation with Robin boundary condition, you usually study it when the parameter beta is a positive parameter. But here we want to not to impose this sign constraint, and we want to study what happens when beta varies in R. The eigenvalue we are interested in is the first eigenvalue, so the one that can be obtained as a minimum of a Rayleigh quotient. As I said, it's a minimum. As in the case of other boundary condition, you can obtain the first eigenvalue as a minimum in W1P of omega of the following Rayleigh quotient. V to the power P. Okay. Until now, there is nothing new, but as there is this Robin boundary condition, you have to add a boundary term. Okay. What we want to do is try to optimize this eigenvalue, so minimize or maximize lambda p beta of omega in a class of admissible set that most of the time will be the open set under some extra constraint that can be, for instance, a measure constraint or a perimeter constraint. Here, the measure will be the classical Lebesgue measure, and the perimeter will be the perimeter in the sense of the Giorgi. Okay, so this is the first goal that we want to achieve, to study a shape optimization problem, because this is an optimization problem that depends on a shape, on a subset of R to the n. But I told you that we want to achieve some further information. Indeed, anytime that a solution, let's call it omega opt, to this problem exists, we want to give some bound to this quantity, lambda p beta of omega minus lambda p beta of omega opt, in terms on a function g that depends on omega and on omega opt. And in some sense, this function, you can imagine it to be like a distance between the two sets. And what we want to do is obtaining some continuity estimate if we can bound the difference between the eigenvalues from above, or a quantitative estimate if we can bound this difference between the eigenvalues from below. And why we are interested in this kind of estimate? Because in a certain sense, this kind of estimate tells us that the problem has more stability. Indeed, if one can prove a continuity estimate, one can obtain the following information. If the set omega is close to the optimal sense with respect to the, let's say, to the topology induced by the function g, the distance g, then also the eigenvalues must be close. That's why I call it a continuity estimate. In the other, from the other part, if we can prove a quantitative estimate, we achieve the following information. We obtain that if the difference between the eigenvalue is closed, also the sets must be closed. And so this is what we want to do, letting beta vary in R. And we will consider mostly 3 cases that have some different behaviors. The first one, when beta is equal to plus infinity. The second one, when beta is positive. And the third one, when beta is negative. What is missing? When beta is 0. Indeed, when beta is 0, the problem becomes trivial. Indeed, we recover, if we forget about this term, the Neumann boundary condition, for which the first eigenvalue is 0 and the first eigenfunction is the constant function. So as we want to optimize the eigenvalue, they are all equal to 0, you have nothing to optimize. Okay. So this is what is very difficult. Okay. I just want to keep this there so that you can keep all this information in mind. Okay. In the first case, when beta is equal to plus infinity, we recover a very well-known problem. Indeed, if you let in that variational formalization beta to go to plus infinity, you see that the contribution on the boundary must be smaller and smaller indeed to have something finite. And so in some sense, the problem is converging to the classical Dirichlet eigenvalue problem. And so we can get rid of the dependence from beta, as we are saying that is minus infinity, plus infinity. And we are minimizing on the Sobolev function that are 0 on the boundary to the power p on omega. Okay. And I told you that we want to minimize or maximize the eigenvalue. In this sense, in this setting, it's meaningful only to do one of the two things. Indeed, what is meaningful to do is to minimize the eigenvalue, or if we impose a measure constraint, or if we impose a perimeter constraint on the set omega. Indeed, if you want to maximize the first Dirichlet eigenvalue under both a perimeter or a measure constraint, you can see that the problem is ill-posed, as you can find a sequence of sets along which the first eigenvalue diverges. Indeed, for instance, in the case p equals 2, n equals 2, it's very easy to, quite easy, not very easy, to compute the eigenvalue on a sequence of rectangle. For instance, if you take the long side to be equal to n and the small one to be equal to 1 over n, you are fixing the measure to be 1, and the eigenvalue, you can see that it goes like pi n, and so it diverges. And you can find, you can do a similar thing also in the case when you fix the perimeter. So in this setting, it's not meaningful to maximize the eigenvalue. What is meaningful is to minimize, and this shape optimization problem has a very well-known solution. Indeed, the Faber-Krahn inequality tells you that among all sets with prescribed measure, so the first one that we are considering is the one with the prescribed measure, the set that minimizes the first p-Laplace Dirichlet eigenvalue is the ball with the same measure as omega, that I will refer to as omega sharp. Okay, so this is a very famous problem, but we have just solved the optimization problem. What if we want to achieve more information? Can we obtain, for instance, a continuity or a quantitative estimate? First of all, this problem is solved among open set with fixed measure. And if we want to obtain a quantitative estimate, then it is possible to obtain it. Indeed, in 2009, Fusco, Maggi e Pratelli proved that you can bound the eigenvalue deficit with a constant that depends on the dimension and on D. I think that it must be normalized in terms of a distance that is called Frankel asymmetry index. And what is this distance? This distance is defined as the L1 distance between omega and a best ball of the same measure as omega. And so this here you have a power that is 2 plus p. Okay, so in this setting, is it possible to prove a quantitative estimate? And what about a continuity estimate? Is it possible? Yeah, please. Yeah. This proof of the isoperimetric of the Faber-Kran inequality strongly relies on the quantitative isoperimetric inequality. Yeah, indeed, you prove it by applying using the geometric the variational characterization, then use some co-area formula and isoperimetric inequality. So it strongly relies on the isoperimetric inequality, and that's why here, for instance, you obtain this power 2 plus p that is not the right power that one should expect. You have to wait some more year to obtain the sharp quantitative Faber-Kran inequality, where Brasco, De Flippis, and Velichkov, I guess, yeah, are able to remove this p. Okay. Can we expect so a continuity estimate? The answer is no. Indeed, there is this famous example of by Ciuranescu and Murat that tells you that if you take, for instance, a ball and you start to perforate it with the smaller and smaller holes that are placed symmetrically, when you send the size of the ball to 0, the set are going to the ball in the L1 distance, but the eigenvalue doesn't go to the eigenvalue on the ball. And so you cannot expect a continuity estimate if one doesn't, at least if one consider open sets, okay? So this is what we have in the case of Dirichlet eigenvalues with fixed volume. What if we consider the eigenvalue problem with the fixed perimeter? Once you have the Faber-Kran, it's very easy to find that when you fix the perimeter, you consider omega, you have omega sharp, and then the ball that has the same perimeter as omega contains omega sharp, and I will denote it by omega star. By the variational characterization, one can see that the eigenvalues are ordered and they are decreasingly ordered. So you easily obtain by the Faber-Kran inequality that once again, the solution to this shape optimization problem is a ball, but of course it's a different ball because you are prescribing the perimeter, not the volume. And so in this setting, what is missing is to prove, for instance, a quantitative result. As in the case of, in the previous case, you can construct a similar example for which you are not able to prove neither a continuity result. But this strange example consists in perforating the set. So what about we prevent this situation to happen? And what is possible to prove if you consider convex set is that you can prove a continuity estimate. So you can prove that when you consider the eigenvalue of the set omega, then the eigenvalue of the ball with the same perimeter, you can bound from above this ratio with a constant that depends on n and on p, times the difference of the measure. But actually, what is this difference between the measure? As this one is the measure of the ball having the same perimeter as omega, this is nothing more than the isoperimetric deficit of omega. So you are able to prove that when you have when you're considering the problem with fixed perimeter, you can prove a continuity estimate if you consider the convex set. And as I told you that the eigenvalue on the ball with the same perimeter as omega controls the eigenvalue on the ball with the same measure as omega, you can obtain also a continuity estimate among a set of fixed measure. And so the Churanescu-Murat example doesn't apply if we consider convex set. So what remains open is trying to understand, okay, I cannot make holes inside the set, but what if we consider, for instance, a simply connected set? This is not known. What is known is that among convex set, is it possible to prove a continuity estimate? So this is more or less what was available in the literature among regarding the Dirichlet eigenvalue. Let us see what happens when Robin eigenvalue comes into play. And what I told you is that you have to distinguish the case when beta is positive and beta is negative. And that's why the two eigenvalues have very different behaviors when you're considering, when you change the sign of omega. Okay, for instance, we will see that when beta is positive, the behavior of this eigenvalue is much more similar to the one of the Dirichlet eigenvalue. Indeed, what you can prove is that you can consider, also in this case, what is meaningful to do is to minimize the first eigenvalue, not to maximize. Well, maybe it's not so easy to explicitly compute the Robin eigenvalue among a sequence of set, but what you can do is prove an inequality that tells you that the first Robin eigenvalue, when beta is positive, is controlled from below by a constant that depends on n, I guess on p, and on beta, 1 plus beta to the power 1 p minus 1. Okay, you should have some power here. There is, okay, you should have some power here that now I don't remember, but okay. What is this quantity that we see here? This is the so-called inner radius of a set omega, and what is the radius of the largest ball that you can put inside omega. So if you take, like before, a sequence of collapsing rectangle, the ball that you can put inside omega becomes smaller and smaller. And if the ball becomes smaller and smaller, also the radius becomes smaller and smaller. And so this function goes to 0, and so the eigenvalue diverges. That's why it's not meaningful to maximize the first Robin eigenvalue also in this case. What is meaningful to do is to minimize it, and they proved, Bossel and Danners, this is from 86, and this is 2006, that if you minimize the first Robin eigenvalue, then you obtain that the solution to this problem is once again a ball if you're keeping the measure fixed. that's why I told you, you have kind of the same behavior of the Dirichlet eigenvalue. And in the previous case, it was very easy to find the solution when you fix the perimeter of a set omega. Why? Because the Dirichlet eigenvalues had that fine rescaling property, that fine monotonicity, the monotonicity that I wrote here. Okay, maybe it's a little bit messy. I know. Okay. In this case, if you look at the variational characterization, you might understand that it's not so easy to prove a monotonicity property. Indeed, and indeed is not true. But luckily, there is a kind of monotonicity formula that tells you that when you take a set omega and you enlarge it in the set that you consider T, the dilatation of omega of a factor T, when T so is greater than 1, then just in this special case, the eigenvalues are ordered. And so the eigenvalue lambda p beta of T of omega is smaller than the eigenvalue of omega. And this is what we need to prove a Faber-Cran type inequality also in the case of the Robin eigenvalue with fixed perimeter, as the sets are the same as before. So once you have a Faber-Cran type inequality, you know that the ball is the best shape when you prescribe the measure. So if you want to prescribe the perimeter, the ball with the same perimeter will be larger, would be a dilatation of the previous ball, and it will be larger. So you can obtain a new Faber-Cran type inequality among sets of fixed perimeter. Okay, so we have solved the shape optimization problem. And also in this case, you can perform an homogenization strategy as before to prove that you cannot, you have no hope to have a continuity estimate in none of these cases. So let us see if we have some quantitative result. Okay. Yeah, you can prove a quantitative result, as in the case of the Dirichlet eigenvalues. Indeed, in 2018, they were Bucur, Perone, Nietzsche, and Trombetti. They prove that if you fix the measure, then you can control the Bosel-Danner's deficit from below by a constant that depends on n, on p. No, actually they prove it for p equal to. From beta and from the measure of omega times the same asymmetry index as before, so the L1 distance between omega and the best ball that covers omega. Here we see something strange. While if we are fixing the measure of omega, the constant that we obtain here depends on the measure of omega. Maybe this estimate is wrong. The problem is that we cannot rescale everything. So we cannot obtain a scaling invariant inequality as we have in the case of the Dirichlet-Laplacian. And so the constant that we have here has to depend on the measure. It's not that these guys here were not good enough to prove the good inequality. So it's the best that you can obtain. And in the previous case, we saw that it was possible to obtain a continuity estimate. And that was possible if one avoids the homogenization thing. Okay. And so also in this case, we proved in collaboration with Vincenzo Amato and Andrea Gentile that if you consider a set omega that is convex, then you can control the difference between the eigenvalue, and here we normalize it, but as we see, it's useless, in terms of a constant that depends on n, on p, and p, beta, and the perimeter of omega, times the difference between the measure of omega and omega sharp. As I said to you before, this is nothing more than the isoperimetric deficit of omega. And also in this case, as we have this beautiful rescaling property, we obtained, just doing one proof, also the continuity of the problem when you're fixing the measure. Okay, so just let us make some comments on this estimate that we proved. Once again, we have a dependence on the perimeter, and we cannot get rid of it, at least in this formulation. We have an explicit formula for this constant, and this explicit formula depends on an eigenfunction on the ball omega star. Indeed, you can write it as the L infinity norm of this eigenfunction, beta on the ball omega star, times divided to the power p divided by the LP norm to the power p. And what we wanted to do was get rid of this dependence on omega. And so, as this constant strongly depends on the eigenfunction of the ball, we started studying the behavior of this eigenfunction on the ball. And what we found is that these eigenfunctions, in a certain sense, are ordered. Of course, the eigenfunctions are defined up to a multiplicative constant. But if you fix the value that the eigenfunction, for instance, if you fix the L infinity norm, we proved that, so let us consider 2 beta 1 less than beta 2, and let us fix the L infinity norm of the two eigenfunctions. What we found is that the function that to beta associated the eigenfunction is decreasing. Yes. in the sense that if beta 1 is smaller than beta 2, then b beta 1 of x is greater or equal than b beta 2 of x pointwise in the ball. Here I'm writing omega star, but it holds for any balls you are considering. And so the constant there depends increasingly on beta. The function then to beta associated the L infinity norm of V beta to the power P over the LP norm to the power P is increasing, and you can find an upper bound to this sequence in terms of beta, and it converges to very surprising to the eigenfunction of the Dirichlet Laplacian on the same ball. And thanks to the very nice property of the Dirichlet Laplacian, this constant can be does not depend on the perimeter of omega. So it is possible to get rid of this constraint, this dependence on the perimeter, and also on beta. Another question that we in the shape optimization community always ask, we are obsessed with, is if the inequality is sharp. In what sense? If the right-hand side and the left-hand side goes to 0 with the same velocity, if, for instance, the set omega goes in a certain sense to, for instance, in the L1 sense, to the ball omega sharp. And what we found is that at least we make the computation for the case p equals 2 because it was easier. And what we found is that if you compute this inequality on a sequence of regular polygon, you obtain that the right-hand side and the left-hand side goes to 0 with the same velocity. And so in this sense, we make the shape optimization people happy. Okay, so this is what we obtain in the case of beta positive. In the remaining time, I would like to tell you about the last case, so the negative beta. And this is the most incomplete case. Okay, there are still a lot of things that needs to be proven. So first of all, the behavior of this eigenvalue problem is a little different. Indeed, the first eigenvalue is not more positive. When you consider beta to be negative, and you choose here in the variational characterization, for instance, a constant function, you obtain a natural upper bound on the eigenvalue in terms of the perimeter of omega and the measure of omega. And as beta is negative, you may see that also the eigenvalue is negative. And so in this case, it's very easy to understand. Well, I don't know, for me it's very easy, so I don't want to be unpolite. Once you have this inequality, maybe you can understand that minimizing the first eigenvalue has no meaning, because you can take a sequence of a set that has, for instance, you can keep the perimeter fixed, and you can send the measure of omega go to 0, or you can do the converse. So you can fix the measure of omega and you let the perimeter goes to plus infinity, and you obtain the first eigenvalue tends to minus infinity. And you can do it just considering the sequence of rectangles that we saw before. Okay, so it's not a matter of not being convex. The problem is not well posed also among convex set. So let us try to maximize this eigenvalue, but we have still some problems. Indeed, for instance, let us fix the measure. You fix the measure, then what would you expect? In all the things that we have seen till now, we saw that a ball was the optimal shape. So in 66, I guess, Berekett conjectured that among open set, at least in the plane, the ball omega sharp has to maximize the first Robenan eigenvalue. And then this is not true, unluckily. Indeed, these two guys, no, I cannot write. They are Freitas and Krejcik, and the second name is so difficult to write, so just remember, please. These two guys prove that when beta goes to minus infinity, the annulus is better than the ball. Oh, of course, you are keeping the measure fixed. So this annular has the same measure as the ball. And this is true. So where for value of beta very large. So the Berekett conjecture cannot be true for any value of beta. But in the same paper, these two guys proved that if beta is sufficiently close to 0, then the conjecture is true, at least among C2 set. And this value here depends once again on the measure of omega that you are fixing. They don't write it explicitly, but they remark that it depends on the measure of omega. So what do we want to prove? We don't have a solution to this problem. We cannot prove a continuity estimate. We cannot prove a quantitative estimate. So please solve this kind of problem so that some other people can prove the remaining thing. So this is the case when you fix the measure. Let us fix the perimeter. Let us see if we have more, if we are more lucky. Yeah. Yeah, maybe it's the. Mm-hmm. Yeah, it's open, you're right. Okay, it's just open. Because now we are going to see where this C2 comes from. Okay, let us fix the perimeter. And this is the last thing that I will let you do, I promise. Okay, what happened? In this case, we are more lucky. Indeed, in 2007, Antunes, Freitas, and Krejcik, the same person as before, proved that in the case n equal 2, the ball maximizes the first eigenvalue, and beta is a negative parameter, among C2 set, and that's where the C2 came from, of fixed perimeter. So we have a Faber-Cran inequality of the reverse type. Okay. Among C2 set of fixed perimeter. I told you. Okay. But this is just one thing that they proved, and we are not happy. And that's why later on in 2019, Bucur, Perone, Nietzsche, and Trombetti proved that the ball is a maximizer, so the same Faber-Cran type inequality holds in any dimension for any P and among convex set. So we have this convexity constraint that comes into play once again. We don't know what happened if the sets are not convex. I'm not so confident to say that there is chance to prove a Faber-Cran type inequality. Okay, and so in this setting, we wanted to prove something. And we proved a quantitative estimate of the same type as before, proving that among convex set in Rn, you can bound the difference between the eigenvalue, and here you see it is reversed because you always consider the absolute value. In terms of a function that depends on n, on p, on beta, and on the perimeter that you are fixing. And you have, once again, the same isoperimetric deficit as before. So you might think, okay, you're proving always the same thing. Yes, because indeed this kind of result, the two results that we obtain in the same paper in collaboration with Andrea Gentile and Vincenzo Amato are obtained with exactly the same technique. And the only thing that you have to be careful about is the difference of the behavior of on the eigenvalue. Also, the constant here is nothing more than the same constant as before. Indeed, here you have the value that the function attains in 0. Sorry, the minimum of the function. Okay, what was the point? This constant depends on the eigenvalue on the ball. Once again, as in the case of beta positive. And it depends through this eigenfunction in this way. You have the minimum of this eigenfunction to the power p over the LP norm. Okay, to the power p. So the LP norm is the same, the denominator is the same that you have before. You may think that this is something different, but if you look at how this eigenfunction behaves on a ball, of course only on the ball, you may see that these eigenfunctions are radially symmetric, and when beta is positive, they are kind of concave, let's say like this, but they are not concave, they are just log concave. Okay, but you may imagine that they have this kind of profile. And I told you that they are ordered if you fix the L infinity norm. That is the value that the eigenfunction assuming 0. Okay, so let's say that we are considering beta 2 greater than beta 1, and you have this inclusion. The same inclusion holds regardless the fact that beta is positive or negative. So you can fix the value that the function assuming 0, and you have the same inclusion as before. So the function that to beta says V beta is increasing in all R. And in the previous case, we were prescribing here the constant when beta was positive depends on the L infinity norm of the eigenfunction. Now it depends on the minimum, but if you see at the picture, they are exactly the value that the eigenfunction assumes in 0. And that's why I told you, yeah, we proved always the same result. And I have some more time. So I would like to tell you that a quantitative estimate already exists. We, in the context of the Robin eigenvalue of the Laplacian, in terms of something else. Indeed, in 2021, Cito e Lamanna proved that if the difference of the eigenvalue, of course, you are considering beta to be negative, you are fixing the perimeter because here is the only way to obtain a Faber-Cran type inequality. And they proved that if the difference between the eigenvalue is small, here the set are rule convex, then you can control it from below with a constant that depends always on n, on beta, on the perimeter that you are prescribing, times a function g of some asymmetry index. And now I'm telling you what are all these characters of omega. Okay, this function g has a very peculiar form, but this will not surprise you because you have already seen it. It is s to the power 2, or is 1/2. Okay. Okay. S to the power 2, if n is equal to 2, is f to the minus 1 of s squared, if n is equal to 3, where this function f is t log t square root. So whenever this inverse function is defined, and then you have s to the power n plus 1 over 2 if n is greater or equal than 4. And this asymmetry index here is the Hausdorff asymmetry index that in a certain sense you can see it as the L infinity distance between the set omega and a best ball of the same perimeter as omega covering omega itself. So how these two results are linked, the one by Cito and Lamanna and the one of ours, in a sense, of course, okay, ours depends on P. Here you have 2, but if you perform the computation, it's not difficult to extend this result to the p-Laplacian case. I would like to say this thing, but please don't be rude to me. Our result seems to be a little stronger in the sense that from our, you can recover theirs exactly as they prove it. So you can prove ours and then obtain as a corollary theirs. What's the advantage of our result? That for me is a real advantage, is that while their proof strongly relies on a Fouglede type approach, I don't know if you're familiar with this kind of Fouglede approach, you consider nearly spherical set, so that kind of set that can be written as a graph over a sphere, and then you make a lot of computation. And I hate this kind of Fouglede approach that Fouglede used to prove the quantitative isoperimetric inequality. Our result didn't make use of this strategy, and we use some symmetrization argument that I'm more familiar with. I like them most simply, but well, it's just a matter of what you like. Okay, so I think that I can conclude here. So if you have some question.
Okay, thank you, Alba Lia, for the nice talk. Are there any questions, comments?
I think I didn't understand the very last thing you said, because maybe I don't really know what is A in that result there.
Okay. I will write it. Okay. You know what is the I will write everything. Oh, okay. Okay. If you consider two, let's say, convex set, you can measure this kind of L infinity distance between B and D in this way, as the inf of the epsilon such that epsilon B contains D and epsilon D contains B. What is the Hausdorff distance? Is the minimum epsilon that you have such that when you enlarge B of size epsilon, you can contain D and vice versa. So this is the Hausdorff distance. And this is very okay to work with the convex set. Okay. The Hausdorff, yeah. No, yeah, it's not the enlarge in the sense that you take B and you add via Minkowski sum a ball.
Che ne so, però il stato liberato nel senso che lavori piccini, nel suo caso dice che i volumi sono piccini.
Yeah, no. Okay. Let's change the notation. C.
Appunto, quindi
So you are enlarging the set and you are till you can cover the other and vice versa. The first time that you can cover both, you have the Hausdorff distance. Now this Hausdorff asymmetry index is defined as the infimum of this Hausdorff asymmetry, Hausdorff distance between omega and a ball that has the same perimeter as omega. In this formulation, you do not normalize, and you are taking the best ball. So you translate this ball here in order to cover as much omega as possible. Okay. And it should be the same the things that Fuglede does in the quantitative isoperimetric inequality. He should have the same function G with the depending on the Hausdorff distance.
Okay, but what I don't understand is what follows. With that inequality, okay, you
How
have to...
you reach
No, wait, because maybe I'm looking at everything in the wrong direction, but if you, from this inequality, if you know that the eigenvalues are closed,
okay,
you get that the volumes are closed, right?
Our result holds in general.
Yes.
Okay. And here you have the isoperimetric deficit. The point is that the isoperimetric deficit controls these things here only if it is small. Okay, and so that's why they need to add a smallness assumption on the deficit, on the eigenvalue deficit.
I see. Okay.
Okay. This also in general,
Okay.
but it's not a quantitative result in the way you are used to. You don't have an asymmetry index.
Okay.
Okay, so it might seem strange.
Okay.
In order to re-obtain a kind of classical quantitative result, we have to take in account that we need a smallness assumption on this term that you recover it if you assume that here you had the eigenvalue deficit. If this is small.
Thank you.